Somewhere in the western Pacific, nearly 7 miles beneath the surface, lies the deepest place on Earth, the Mariana Trench. The first humans reached its floor in 1960. The second descent did not happen until 52 years later. It has become the most famous geological feature in the ocean, a place so extreme that its name has become synonymous with the unknown. And yet, in its entire recorded history, the Mariana Trench has never generated a catastrophic tsunami, not once. The plates beneath it are so weakly coupled that for decades, scientists questioned whether the Mariana subduction zone was even capable of producing the kind of giant megathrust earthquake that devastates coastlines. By the measure that matters most to the people living above the ocean, the world's deepest trench is also one of its quietest. While the Mariana captured the world's imagination, other trenches were doing something it cannot. They were rupturing fault lines hundreds of miles long. They were lifting and dropping enormous sections of the seafloor in minutes. They were launching walls of water across entire ocean basins at the speed of a commercial jet. One trench, more than 12,000 feet shallower than the Mariana, produced the deadliest geological disaster in modern human history. Another shifted its own seafloor 164 feet in just 11 minutes. Another has spent centuries sending Pacific-wide tsunamis toward Hawaii and the western coast of North America. Another lies north of more than 4 million American citizens, while producing the most extreme gravity anomaly ever measured anywhere on Earth's surface, and most of those people have never heard its name. The Mariana is extraordinary. It deserves every documentary ever made about it, but it is not the ocean's most dangerous trench. Not even close. Tonight, we're leaving the world's deepest trench behind to uncover 5 far less famous trenches, each with a different history of geological violence, and why the greatest dangers on the ocean floor have almost nothing to do with depth. But before we do, let me know in the comments, where are you watching from today, and what is the time over there? Reading your comments and seeing where you all are watching from is one of my favorite things to do. Now, let's descend toward the fault lines that changed history. Far beneath the rolling surface of the sea, the shape of the ocean floor folds into a long, narrow depression where one immense slab of the planet begins disappearing beneath another. That depression is an ocean trench, not a crack torn open, but the visible crease formed where 2 tectonic plates meet, and one is gradually forced downward into the mantle. It is a boundary measured not only in distance, but in time, because the movement unfolds across centuries before revealing itself in moments. The descending plate does not glide beneath its neighbor with effortless motion. Along the boundary where the 2 surfaces press together lies a vast fault known as the megathrust. Friction binds portions of that fault so firmly that motion nearly stops, even as the surrounding plates continue their steady journey. Year after year, the rock bends without breaking, storing elastic strain much like a branch flexing beneath increasing weight. The surface appears unchanged, yet energy continues gathering beneath it with unwavering patience. Eventually, the accumulated strain exceeds the strength of the locked fault. At that instant, the restraint gives way. Rock that resisted motion for generations suddenly shifts in a matter of minutes. Entire sections of the boundary can lurch dozens of feet at once, releasing more energy than any other category of earthquake found on Earth. The event is known as a megathrust earthquake, and its consequences depend less on the depth of the trench than on the character of the fault itself. When rupture reaches the shallow portion of the plate boundary, the ocean floor above it is lifted or dropped almost instantly. The water resting overhead cannot remain where it was. An immense pulse of displaced seawater begins racing across the basin, carrying energy through the entire depth of the ocean. The resulting tsunami is born not from wind or weather, but from the sudden movement of the planet's crust. From the first fracture beneath the seabed to waves arriving along distant shores, the sequence unfolds with remarkable speed. Several hidden characteristics determine whether a trench can produce such events. One is coupling strength, the degree to which the converging plates cling together instead of slipping past one another. Strong coupling allows enormous stress to accumulate before release. Another is the architecture of the sediments covering the fault. In some places, those sediments help absorb movement before it reaches the seafloor. Elsewhere, they allow rupture to continue upward, transferring far more motion into the ocean above. The pace of plate convergence also shapes the future of a trench. Faster motion replenishes stored strain more rapidly, shortening the geological interval required before another great release becomes possible. Geography completes the picture. A powerful earthquake beneath an isolated stretch of ocean presents a different level of hazard than one occurring beside coastlines where millions of people live within reach of an incoming tsunami. One feature rarely appears among these governing factors. Depth, despite its fascination, says remarkably little about destructive potential. The depth of a trench reflects the age, density, and angle of the descending plate. Older, colder crust sinks more steeply into the mantle, carving deeper trenches as it descends. That geometry may create spectacular depths, while reducing the broad areas of friction needed for the largest megathrust ruptures. The Mariana Trench illustrates this contrast with remarkable clarity. There, the Pacific Plate descends at an unusually steep angle after becoming exceptionally old and dense. The contact between the plates is comparatively limited, weakening their mechanical coupling. Rather than locking together across an extensive interface, they tend to release strain in smaller, more distributed ways. The very arrangement that produces the deepest trench on Earth also restrains the conditions required for the greatest tsunami-generating earthquakes. Many of the world's most hazardous trenches follow a different design. Their plates descend along gentler slopes, creating broad zones where friction locks vast sections of crust together. Carefully layered sediments can permit rupture to extend all the way to the seafloor, multiplying the movement transferred into the ocean above. Their danger comes not from extraordinary depth, but from the hidden mechanics of contact, pressure, and release that continue beneath the waves every passing day. Across the eastern margin of the Indian Ocean, the coastline of Sumatra bends gently toward Java, tracing the edge of a boundary that has been reshaping the region for millions of years. Just beyond the reach of ordinary maps, the Sunda Trench follows that curve beneath the sea, marking the place where the Indo-Australian Plate descends beneath the Eurasian Plate. The movement is almost imperceptible, advancing only about 2½ inches each year, yet every passing season adds another fraction of stored strain to a fault that stretches for hundreds of miles. It is not the deepest trench in these waters. It has become the one whose history altered humanity's understanding of the ocean itself. On the morning of December 26, 2004, that long accumulation of strain reached its limit. A rupture measuring between magnitude 9.1 and magnitude 9.3 burst across more than 930 miles of the Sunda megathrust beneath the Indian Ocean. Beginning in the south and racing northward, the fracture released one of the 3 greatest earthquakes recorded since worldwide seismic monitoring began during the 1890s. Entire sections of the fault shifted at once, with portions in the southern rupture zone slipping by more than 98 feet before settling into a new position deep beneath the sea. The movement did not remain hidden below the seafloor. Vast areas of the ocean floor were lifted by as much as 33 feet, forcing the overlying water upward in a single geological moment. From that sudden displacement emerged a tsunami that crossed the Indian Ocean at speeds approaching 500 miles per hour. Along the coast of Aceh in northern Sumatra, the incoming waters surged to heights reaching about 167 feet. Communities that had greeted an ordinary morning found the shoreline transformed before the scale of the event could be understood. The waves spread outward across the basin with astonishing reach. Less than 2 hours after the earthquake, they arrived on the shores of Sri Lanka. Within roughly 7 hours, they had crossed more than 3,000 miles to the coast of Somalia, carrying the imprint of the same rupture across an entire ocean. Beaches in Thailand, separated from the fault by open water and unfamiliar with the name of the trench beneath it, became part of the same geological story. By the time the sea settled once more, approximately 230,000 lives had been lost, while nearly 1,700,000 people had been displaced, making it the deadliest tsunami in recorded human history. The extraordinary scale of the disaster did not arise from earthquake magnitude alone. Beneath the waters of the trench rested an immense blanket of ancient sediment delivered over countless ages from the Ganges River system. This enormous accumulation, known as the Nicobar fan, created an unusually firm wedge above the megathrust. In many subduction zones, thick sediments can soften the transfer of movement before it reaches the seafloor. Here, the structure behaved differently. It transmitted the rupture efficiently toward the surface, allowing the seafloor to rise more dramatically and giving the tsunami far greater power than might otherwise have developed. Even this immense event belonged to a much older sequence. In 1861, another great earthquake had ruptured part of the same fault system, leaving evidence in both historical accounts and coastal landscapes. Far beyond written memory, layers of marine sand preserved across Sumatra reveal earlier tsunamis from the Sunda Trench, each deposited by oceans that crossed the land and later withdrew, leaving thin records beneath forests and wetlands for future generations to uncover. Before 2004, many scientists regarded the hazard posed by the Sunda Trench as lower than it truly was. The earthquake transformed that understanding. During the following decade, more than 6,000 aftershocks exceeding magnitude 4.5 rippled through the surrounding crust, followed by additional major earthquakes measuring magnitude 8.6 and magnitude 8.4. Together, they revealed the remarkable extent of the plate boundary, replacing assumptions with direct evidence written across one of Earth's most consequential fault systems. The memory of a great rupture can create the impression that a fault has finally spent its strength, as though the release of so much accumulated energy leaves little behind. Beneath the Sunda Trench, the geology tells a different story. Earthquakes do not empty an entire plate boundary in a single motion. They redistribute stress, alter neighboring segments, and begin another interval of gradual loading almost as soon as the ground settles. The movement of the plates never pauses, and neither does the slow rebuilding of strain. The immense earthquake of 2004 fractured only part of the Sunda megathrust. South of the main rupture lies the Mentawai segment, extending offshore from western Sumatra. Measurements made with networks of precise positioning instruments reveal that much of this section remains firmly locked. Although the plates continue pressing together year after year, the fault itself has resisted the steady motion, allowing elastic strain to accumulate within the surrounding crust rather than being released through gradual sliding. Historical accounts suggest that this segment has broken before. In 1797, a great earthquake occurred along the Mentawai portion of the plate boundary, producing a major tsunami that swept across nearby coastlines. That event forms one chapter in a much longer geological sequence. Each rupture relieved stress for a time, yet the relentless convergence of the plates ensured that the process would begin again. More than 2 centuries later, the same section continues storing energy beneath the floor of the Indian Ocean. For this reason, many Earth scientists regard the Mentawai segment as one of the highest priority seismic gaps on the planet. A seismic gap is not a promise that an earthquake will happen soon. Instead, it identifies a portion of an active fault where accumulated strain appears substantial compared with neighboring sections that have ruptured more recently. It is a recognition of imbalance rather than prediction, reflecting what can be measured rather than what can be scheduled by nature. The Sunda system itself is divided by enduring features carried into the trench on the descending oceanic plate. Ancient fracture zones, together with submerged volcanic mountains, known as seamounts, interrupt the otherwise continuous boundary. These structures influence how rupture spreads by creating natural divisions within the fault. During some earthquakes, they act as barriers, slowing or halting the fracture before it reaches the next segment. As decades of observation have shown, those divisions are influential but not absolute. If enough stress accumulates, a sufficiently large rupture can cross them and continue into neighboring sections, linking areas that once appeared separate. Knowledge gained after 2004 transformed preparation throughout the Indian Ocean basin. Nations bordering these waters established extensive warning systems built from earthquake monitoring stations, deep ocean pressure sensors, communication networks, and evacuation planning. Information now travels across continents with remarkable speed compared with earlier decades. Yet every warning system remains constrained by the same physical reality. The earthquake must first occur. Instruments must recognize its characteristics. Specialists must evaluate the data. Alerts must be issued, and coastal communities must receive and act upon those warnings before the sea arrives. Time is generous for waves traveling across an entire ocean, but it becomes scarce for communities situated close to the source. Along parts of Aceh province during 2004, the interval between rupture and the arrival of destructive water was less than 15 minutes. In some locations, the first surge reached shore before organized warnings could have been delivered by any system available at that time. Distance, more than technology, often determines how much opportunity exists to respond. Today, the Sunda Trench remains under continual scientific observation, not because its behavior is mysterious, but because its history is increasingly well understood. The fault has already revealed the immense consequences of a fully coupled plate boundary, while portions of the same system continue accumulating strain beneath the ocean floor. Each passing year adds another small increment to a process measured across generations, reminding us that geological time advances with remarkable consistency, even when human attention shifts elsewhere. Long before modern instruments watched the seafloor with remarkable precision, generations living along the eastern coast of Japan understood that the ocean could sometimes rewrite the landscape in a single day. Offshore, less than 100 miles from the mainland, the Japan Trench marks the place where the Pacific Plate descends beneath the North American Plate. Their convergence continues at roughly 3 1/3 inches each year, adding another almost invisible layer of strain to a boundary that has remained active throughout the geological record, preserved beneath coastal plains and offshore sediments. On March 11th, 2011, that persistent movement culminated in a magnitude 9.0 megathrust earthquake. The rupture unfolded beneath the Pacific Ocean, releasing extraordinary energy along the plate boundary. More than 18,000 people lost their lives, Entire communities along the Tohoku coastline were devastated, and the cascading effects of the tsunami triggered the Fukushima Daiichi nuclear disaster. Yet as scientists examined the event in the months that followed, they discovered that the earthquake had revealed something even more profound than its immense size. For many years, prevailing models suggested that rupture, approaching the shallowest part of a subduction zone, would gradually weaken as it encountered thick sediments near the trench. Friction and deformation were expected to consume much of the remaining motion before it reached the seafloor. The Japan Trench behaved differently. Careful analysis of recovered samples and detailed investigations identified a remarkably thin layer of clay-rich material just beneath the seabed. Rather than resisting movement, this layer dramatically reduced friction along the fault, allowing the rupture to continue almost uninterrupted toward the trench itself. That subtle geological feature transformed the entire character of the earthquake. Instead of losing strength while rising through the shallow fault, the rupture reached the trench axis and displaced the seafloor directly. The distinction may appear modest on paper, yet beneath an ocean, it determines how efficiently energy passes into the overlying water. When the fault reaches the surface of the Earth itself, the seafloor becomes an active participant in the earthquake rather than merely a boundary resting above it. Measurements collected before and after the event confirmed just how extraordinary that movement had been. Near the outermost portion of the overriding plate, sections of the seafloor shifted approximately 164 feet horizontally while rising about 33 feet. The displacement extended all the way to the trench axis, demonstrating that the fault had ruptured completely to the surface. The ocean above could only adjust by lifting and spreading outward, giving rise to a tsunami whose scale exceeded many earlier expectations based on earthquake magnitude alone. Direct observations from crewed submersibles later descended into the trench to examine the transformed landscape. At depths approaching 24,600 feet, researchers encountered a newly formed fault scarp rising about 26 feet above the surrounding terrain. Geological evidence indicated that the shallow fault itself had slipped somewhere between 260 feet and 390 feet. Areas of the trench floor that had once been comparatively level and covered with sediment now displayed fresh ridges reaching nearly 165 feet high. Features, shaped gradually across thousands of years, had been rearranged within minutes. Along approximately 330 miles of coastline, traces left behind by the tsunami recorded water levels exceeding 33 feet above sea level. In the Sanriku region, where the coastline funnels incoming waves into narrow bays, run-up heights surpassed 65 feet. The interaction between coastal geography and the immense displacement beneath the sea concentrated the energy in ways that varied dramatically from one community to the next, leaving a complex geological signature as well as a human one. The Japan Trench became more than the source of a devastating earthquake. It reshaped scientific understanding of shallow megathrust behavior by demonstrating that an unexpectedly weak clay-rich layer could permit rupture to travel directly to the trench axis. A mechanism once considered unlikely had revealed itself through observation rather than theory, encouraging researchers to reconsider other subduction zones where similar conditions may remain concealed beneath the seafloor, awaiting careful study across the slow passage of geological time. Nothing within a subduction zone remembers an ending. Every great earthquake marks the close of one geological interval while beginning another. Beneath the Japan Trench, the Pacific Plate continues its patient descent beneath the North American Plate with the same steady pace that existed before the earthquake of 2011. The release of centuries of stored strain altered the balance of forces along the fault, yet it did not interrupt the larger motion of the planet. From the moment the rupture ceased, the long process of accumulation quietly, though not using forbidden word. Oops cannot use quietly. Rewrite. From the moment the rupture ceased, the long process of accumulation resumed without pause. The portions of the megathrust that slipped dramatically during the earthquake immediately began storing new strain as the plates continued converging. Nearby sections that remained unbroken also experienced important changes. Detailed studies indicate that an area lying just south of the principal rupture received additional stress transferred from the earthquake itself. Rather than releasing that energy during the event, the segment retained it, while the surrounding fault adjusted to its new configuration. For this reason, researchers continue to examine the region as a place where future large earthquakes deserve careful attention, not because their timing is known, but because the mechanics of stress redistribution are now better understood. The events leading into the catastrophe also reshaped scientific thinking about earthquake preparation. 2 days before the main rupture, a magnitude 7.3 earthquake struck offshore. At the time, it appeared to be another substantial but familiar event within an active seismic region. The far larger rupture that followed arrived without additional indications capable of revealing its extraordinary scale. Japan maintained one of the most sophisticated seismic monitoring systems on Earth, with dense instrument networks observing even subtle movements beneath the islands and surrounding seas. Those remarkable systems detected the earthquake almost instantly once it began, yet they did not foresee that it would become one of the greatest ruptures ever recorded. Observation and prediction remained profoundly different challenges. Far below the waves, another transformation unfolded beyond immediate human attention. The violent shaking disturbed enormous quantities of fine-grained sediment resting along the trench slope. Rich in organic matter accumulated over long intervals, these deposits cascaded into the deepest part of the trench. Scientists estimate that more than 1 teragram of organic carbon descended into the hadal environment during this single event. Material gathered gradually across generations arrived on the trench floor within minutes, changing the chemical conditions that sustain deep marine communities and altering biological activity for years afterward. The earthquake, therefore, became more than an episode of crustal movement. It reorganized the ecology of one of Earth's deepest environments through the transport of nutrients and buried organic material. Creatures living far beyond the reach of sunlight encountered a transformed landscape shaped not by gradual settling, but by a brief geological pulse. The relationship between tectonics and biology became visible in a way few natural events can reveal, connecting the movement of continental plates with microscopic processes unfolding thousands of feet below the ocean surface. Evidence of earlier catastrophes had been waiting beneath layers of sediment long before modern instruments existed. Repeated underwater landslides, generated by ancient earthquakes, created deposits known as turbidites, forming a natural archive across the seafloor. Those layers preserve a chronology extending through thousands of years, recording recurring episodes of extraordinary shaking. Among the most significant was the Jogan earthquake of 869, whose tsunami left geological signatures closely resembling those produced during 2011. Together with historical writings, those deposits demonstrated that devastating waves had reached these shores before, providing knowledge that later generations could study even when living memory had faded. Since the disaster, seawalls have been strengthened, evacuation routes redesigned, and many coastal communities rebuilt on higher ground. Portions of Japan's shoreline now reflect lessons learned through both historical records and geological evidence. Yet beneath those carefully planned defenses, The plate boundary continues its measured descent, adding one more fraction of stored strain with every passing year, following the enduring rhythm that has shaped the trench across countless generations. Seen from high above the northern Pacific, the chain of the Aleutian Islands forms a sweeping arc between Alaska and the edge of Asia, as though the ocean itself had been gently bent into a broad crescent. Beneath that graceful curve lies the Aleutian Trench, where the Pacific Plate descends beneath the North American Plate along a boundary extending for roughly 2,485 miles. Its shape is more than a geographical curiosity. The curve influences the direction in which tsunami energy spreads, guiding powerful waves outward across the open Pacific while directing much of their momentum toward the Central Ocean, including the Hawaiian Islands. Across nearly the entire length of this immense subduction zone, the steady convergence of the plates has generated major earthquakes throughout recorded history. Unlike shorter fault systems that release energy within more limited regions, the Aleutian boundary contains numerous segments capable of rupturing independently or in combination. During only the past century, several earthquakes exceeding magnitude 8 have originated along this arc, and many produced tsunamis that traveled far beyond Alaska. Their effects reached distant coastlines, separated from the source by thousands of miles of uninterrupted water, demonstrating that the Pacific Ocean can connect rather than isolate the communities surrounding it. Among these events, the Great Alaska Earthquake of 1964 remains one of the defining moments in modern seismology. Measuring magnitude 9.2, it stands as the second largest earthquake recorded since precise instrumental observations became possible. The rupture occurred near Kodiak Island, where enormous sections of the plate boundary shifted beneath southern Alaska. Land rose in some places and subsided in others, while the disturbed seafloor displaced vast volumes of seawater. The resulting tsunami crossed the Pacific Basin, reaching shorelines far removed from the earthquake itself and causing destruction across communities that never experienced the shaking beneath the ocean. An earlier event had already demonstrated the remarkable reach of this trench. In 1946, a major earthquake within the Aleutian Arc generated tsunami run-up heights, approaching 130 feet near its source. Although the greatest effects occurred close to the rupture, the waves continued outward without exhausting their energy. They reached the Hawaiian Islands and even the Marquesas, carrying the signature of the Aleutian boundary across immense distances. More than 2,300 miles of open water separated the trench from Hawaii, yet the ocean preserved the waves' momentum with extraordinary efficiency. The consequences in Hilo became a lasting reminder of that connection. The tsunami of 1946 claimed 159 lives there, reshaping scientific understanding of distant source hazards. 14 years later, another destructive tsunami reached Hawaii after the Great Chilean Earthquake of 1960. Although generated by an entirely different subduction zone, it traveled across the same broad geometry of the Pacific Ocean and claimed 61 additional lives. Together, these events demonstrated that the islands occupy a position repeatedly exposed to tsunami energy arriving from powerful plate boundaries around the Pacific Rim. The Aleutian Trench continued adding chapters to that history. In 1957, a magnitude 8.6 earthquake generated waves ranging from approximately 20 feet to 40 feet across parts of the Aleutian Islands and Hawaii. More recent geological investigations have expanded that perspective even further. Numerical models combined with ancient tsunami deposits preserved in the eastern Aleutians indicate that prehistoric earthquakes along the same segment may have produced megathrust slip approaching 105 feet. Those ancient ruptures exceeded anything contained within the relatively brief span of written observations, revealing that the historical record captures only a fraction of the trench's longer behavior. When viewed across the entire Pacific, the Aleutian Trench occupies a unique place among Earth's great subduction systems. Its immense length, repeated production of powerful earthquakes, and orientation toward densely inhabited coastlines combine into a pattern unmatched by any other single fault boundary. Alaska, Hawaii, the western shores of the United States and Canada, and the Pacific coast of Japan all share an enduring relationship with this sweeping arc beneath the Northern Ocean, where the gradual descent of one tectonic plate continues shaping the rhythm of waves across an entire basin. Some of the greatest surprises in geology emerge not from places already feared, but from places long regarded as comparatively stable. Within subduction zones, scientists often distinguish between segments that remain tightly locked and those that creep. A creeping fault moves gradually, releasing stress through continuous motion instead of storing it across centuries. That steady movement has generally been interpreted as a reassuring sign, suggesting that little elastic strain remains available for the kind of sudden rupture capable of generating the largest earthquakes and tsunamis. For many years, that understanding shaped hazard assessments along part of the Aleutian Trench. Between the rupture zones of the great earthquakes of 1946 and 1957 lay a section believed to be creeping, because measurements indicated ongoing motion rather than prolonged locking. It appeared to form a natural divider between neighboring fault segments. The prevailing view held that this portion of the plate boundary reduced rather than increased regional danger by preventing ruptures from spreading farther along the trench. Evidence gathered from the landscape began telling a more complicated story. Geological fieldwork across islands in the eastern Aleutians uncovered ancient tsunami deposits preserved within coastal sediments. Layer after layer recorded repeated incursions of the sea far beyond the reach of ordinary storms. Their ages revealed that several exceptionally large tsunamis had originated from a section now regarded as comparatively benign. Instead of confirming long-held assumptions, the deposits suggested that the creeping segment itself had generated destructive events capable of crossing the Pacific Ocean. Those discoveries prompted a broad reevaluation of earthquake and tsunami hazards throughout the eastern Aleutian subduction zone. The ancient deposits indicated that the present behavior of a fault does not always represent its long-term character. Geological systems evolve across centuries, and conditions observed during the brief span of instrumental monitoring may capture only one interval within a much longer cycle. A segment displaying gradual motion today may have behaved very differently several hundred years ago, leaving evidence not in written history, but in buried layers of sand and marine sediment. Numerical modeling strengthened that conclusion. Studies comparing prehistoric tsunami deposits with simulated earthquake scenarios indicated that great ruptures during the 14th, 15th, and 18th centuries involved alternating patterns of deep and shallow megathrust slip approaching 105 feet. Each event produced tsunami inundation in Hawaii, despite originating thousands of miles away. Among them, the 14th century earthquake appears to have generated consequences exceeding those associated with the well-documented event of 1957, revealing that some of the largest episodes occurred before systematic historical observation became possible. These findings carry implications extending beyond a single stretch of coastline. They suggest that the boundaries scientists use to divide major faults into separate segments may represent tendencies rather than permanent limits. Features that interrupt rupture during one earthquake may be crossed during another if conditions permit. Likewise, a section interpreted as creeping from modern positioning measurements cannot automatically be assumed incapable of producing major tsunamis over longer geological timescales. The trench preserves a memory extending far beyond the duration of contemporary observation. Communities bordering the Pacific continue to incorporate these lessons into hazard planning. Along the coast of California, assessments of distant source tsunami risk consistently identify the Alaska Aleutian subduction zone as one of the principal regions of concern. Even though the earthquakes originate far offshore and thousands of miles away, the geometry of the Pacific allows tsunami energy to travel efficiently toward North American shores. As sea levels continue rising through the coming century, the same incoming waves may reach farther inland than they do today, increasing potential impacts without requiring larger earthquakes. The Aleutian Trench itself has shown no sign of geological inactivity. In July of 2020, the Shumagen earthquake, measuring magnitude 7.8, struck another section of the subduction zone and prompted tsunami alerts across much of the Pacific. Although the event proved far less destructive than the largest historical ruptures, it served as another reminder that motion continues along this immense boundary without interruption. Between the great earthquakes remembered by history, the trench remains engaged in the steady work of reshaping the northern Pacific, one measured increment of plate movement at a time. At the boundary between familiar maps and largely unexplored seafloor lies a place where the Atlantic reaches its greatest depth. The Puerto Rico Trench extends north of Puerto Rico and the Virgin Islands, descending beyond 27,300 feet beneath the ocean surface. Hidden within those immense depths is one of the most intricate plate boundaries on Earth, where the North American plate meets the Caribbean plate through motions that resist simple description. Millions of people live only a short distance from this submerged frontier, often without realizing that one of the Atlantic Ocean's most active tectonic systems lies just beyond the horizon. Among the many measurements collected from this region, one stands apart from every other place on the planet. The Puerto Rico Trench is associated with the strongest negative gravity anomaly ever observed on Earth, reaching approximately -380 milligauss. Gravity varies slightly from place to place because the planet's mass is distributed unevenly beneath the surface. In this corner of the Atlantic, the unusually low measurement indicates that powerful geological forces continue shaping the crust far below the sea. Scientists agree that the anomaly reflects active deformation, yet the complete explanation remains incomplete despite decades of investigation. Unlike many famous subduction zones, the geometry here is remarkably complicated. The North American plate does not simply descend beneath the Caribbean plate at a straightforward angle. Instead, the plates converge obliquely, combining downward motion with substantial sideways movement. Portions of the boundary behave like a classic subduction zone, while neighboring sections accommodate horizontal displacement through large strike-slip faults. This mixture of tectonic styles creates a patchwork of interacting structures whose behavior is considerably more difficult to evaluate than simpler plate boundaries elsewhere around the globe. Along the coastlines of Puerto Rico and the United States Virgin Islands, roughly 4 million citizens of the United States live within reach of earthquakes and tsunamis generated by this active boundary. A sufficiently large rupture offshore could produce destructive waves capable of affecting not only nearby islands, but also portions of the Atlantic coastline farther north. Although the Atlantic has experienced fewer basin-wide tsunamis than the Pacific, the physical processes governing wave generation remain the same whenever large sections of the seafloor are displaced. The historical record confirms that this region has repeatedly generated powerful earthquakes. Hazard assessments prepared by the United States Geological Survey indicate that the probability of damaging ground shaking in Mayagüez, Puerto Rico, is comparable to that of Seattle, Washington, another city well known for seismic risk. Historical evidence also points toward a major earthquake during 1787, estimated near magnitude 8.1, that may have originated within the Puerto Rico Trench itself. Later, in 1946, a magnitude 8.1 earthquake north of Hispaniola generated a devastating tsunami. The waves advanced inland across parts of the coastline, and nearly 1,800 people lost their lives before the sea withdrew once again. Beneath these events lies the remarkable gravity anomaly that continues attracting scientific attention. Its greatest intensity occurs roughly 31 miles south of the trench axis, where water depths approach 26,000 feet. In 1977, geophysicist Peter Molnar proposed that this extraordinary signal might result from a massive hanging flap of dense Atlantic lithosphere pulling downward beneath the trench. His interpretation offered an elegant explanation for the unusual measurements, although subsequent investigations have revealed additional complexities. Modern observations continue refining that picture, suggesting that several interacting processes may contribute to the remarkable gravitational signature rather than a single mechanism alone. Compared with the Sunda, Japan, or Aleutian trenches, the Puerto Rico Trench has produced fewer documented giant ruptures during recorded history. That distinction, however, reflects the limitations of observation as much as the behavior of the fault itself. Much of the trench lies beneath some of the deepest and least surveyed waters in the Atlantic, where direct geological evidence remains comparatively scarce. Recognizing those uncertainties, the United States Geological Survey established a dedicated Caribbean earthquake and tsunami hazard program. As detailed mapping expanded across the seafloor, researchers documented previously unrecognized faults and complex tectonic structures, revealing that this profound Atlantic trench still holds many chapters of its geological story beneath the deep ocean. Not every tsunami begins with the unmistakable rupture of a great fault. Along the northern edge of Puerto Rico and the Virgin Islands, another process has been unfolding across immense stretches of geological time, one that depends as much upon gravity as upon tectonic motion. Here, the margin overlooking the Puerto Rico Trench is bordered by towering submarine escarpments, where ancient limestone rests above some of the deepest water in the Atlantic. These submerged slopes preserve evidence that the ocean floor can fail in ways entirely separate from the largest earthquakes. Detailed mapping of the seafloor has revealed slope failures scattered across the edge of the broad carbonate platform extending north of the islands. This platform is composed of thousands of feet of limestone and reef material accumulated through countless generations of marine life, gradually transformed into solid rock over millions of years. While its upper surface appears comparatively stable from above, its outer margin descends toward the trench with remarkable steepness. In several locations, the underwater slopes exceed 45 degrees, creating conditions far more favorable for rapid collapse than those found along most continental margins bordering the United States. The platform itself has not remained perfectly level throughout its history. As tectonic forces slowly reshaped the northeastern Caribbean, the entire limestone mass gradually tilted toward the trench. That prolonged movement placed increasing stress upon the fractured cliffs lining its northern edge. Cracks developed within the rock, faults dissected older formations, and gravity continued acting upon every unstable block. Each passing century added another subtle adjustment, preparing sections of the platform for future failure, even when no major earthquake occurred nearby. Oceanographic surveys uncovered extensive fissures near these submarine cliffs, indicating that collapse remains an ongoing geological process rather than an ancient event completed long ago. During the same investigations, researchers identified enormous submarine landslides on the northern side of the Puerto Rico Trench that had never previously been documented in such detail. Some of these ancient failures involved volumes of displaced sediment and rock large enough to generate tsunamis through their own motion. Instead of depending upon broad fault rupture beneath the seafloor, the rapidly descending mass itself displaced seawater and initiated powerful waves. A submarine landslide tsunami follows a different sequence from one generated directly by tectonic fault movement. The collapse may occur after gradual weakening, changes in groundwater within the rock, additional sediment accumulating upon unstable slopes, or comparatively modest shaking insufficient to trigger widespread seismic alarms. Because the source lies so close to nearby coastlines, the resulting waves can reach land within only a few minutes. In such circumstances, the interval available for detection, communication, and evacuation may become extraordinarily brief, regardless of how advanced monitoring technology has become. Numerical simulations examining possible failures within the Puerto Rico tectonic system illustrate the seriousness of this secondary hazard. Some modeled scenarios produce waves approaching 33 feet in height, with flooding extending as much as 2.5 miles inland across vulnerable portions of Puerto Rico and the United States Virgin Islands. Local geography strongly influences the ultimate extent of inundation, yet the combination of steep submarine slopes and nearby coastal communities creates conditions where relatively localized failures may still produce severe consequences. Further evidence of the platform's long history of collapse appears in the form of immense amphitheater-shaped scars preserved along its northern margin. Two of these features measure between 18 and 30 miles across, marking places where extraordinary volumes of limestone detached and descended into deeper water long ago. Whether those ancient collapses were initiated by powerful earthquakes or developed through spontaneous structural failure remains an active area of scientific investigation, reminding researchers that more than one geological pathway may produce similar landscapes. Historical experience offers another glimpse of this complex hazard. In 1918, a magnitude 7.3 earthquake within the Puerto Rico fault system generated damaging shaking and a tsunami that claimed 116 lives in northwestern Puerto Rico. Geological evidence indicates that submarine landslides contributed to the event alongside the earthquake itself, demonstrating how multiple natural processes can unfold together. Along the Puerto Rico Trench, the movement of tectonic plates, the pull of gravity upon fractured limestone, and the immense weight of the surrounding ocean combine into a geological system whose hazards arise through more than a single mechanism. Movement defines the Tonga-Kermadec Trench more than any single moment in its history. While many Great Plate boundaries advance at a pace measured almost reluctantly across the ages, this one presses forward with unusual urgency. From the islands of New Zealand northward, through the Kermadec Arc, and onward toward Tonga, the boundary stretches for roughly 1,740 miles, marking one of the most energetic regions on the planet. Every passing year adds another small advance to a process that has continued for tens of millions of years without interruption. Within this immense system lies Horizon Deep, the second deepest known location in the world's ocean. Its floor descends beyond 35,700 feet beneath the sea, surpassed only by the deepest point within the Mariana Trench. Even beyond horizon deep, much of the Tonga-Kermadec Trench remains deeper than 32,800 feet, making it the deepest seafloor region in the southern hemisphere. The scale of these depths creates an environment where sunlight never arrives. Pressure rises to extraordinary levels, and the descending tectonic plate continues its journey far beneath the ocean floor. The remarkable pace of that descent distinguishes this trench from nearly every other subduction zone on Earth. Here, the Pacific Plate moves beneath the Indo-Australian Plate at approximately 9.4 inches each year, making it the fastest known plate convergence presently measured. That speed is nearly 4 times greater than the convergence observed along the Sunda system. Although a few additional inches may appear insignificant over the course of a single year, geological time transforms that modest annual motion into hundreds of feet of accumulated displacement, continually reshaping the boundary between the two plates. The importance of this rapid convergence extends well beyond simple movement. Wherever the fault interface becomes locked, stress accumulates more quickly because the plates continue attempting to move, despite remaining temporarily stuck together. Faster convergence, therefore, shortens the interval required to rebuild significant strain after previous ruptures. The Tonga system continually stores and releases tectonic energy through recurring earthquakes, maintaining a rhythm dictated by one of the swiftest plate motions anywhere on the globe, rather than by prolonged geological stillness. The descending Pacific Plate also follows an unusually steep path into Earth's interior. Its dip commonly ranges between approximately 40 and 50 degrees before continuing downward to depths approaching 1,000 miles beneath the surface. Few subducting slabs penetrate so deeply into the mantle while remaining identifiable through seismic imaging. Geological evidence indicates that this process has continued for roughly 45 million years, allowing an immense volume of oceanic lithosphere to descend into the planet's interior while steadily influencing the circulation of mantle material below. Running beside the trench is another expression of that persistent motion. More than 30 active or recently active volcanoes form a sweeping volcanic arc parallel to the plate boundary. Many remain concealed beneath the ocean, constructing volcanic cones through repeated eruptions before portions of those structures eventually collapse and are rebuilt once again. Their activity reflects water released from the descending plate, lowering the melting temperature of surrounding mantle rocks and generating magma that rises toward the surface through fractures in the overlying crust. The same geological engine also produces an extraordinary range of earthquakes. The Tonga subduction zone contains the most active concentration of deep earthquakes known anywhere in the world, with seismic events occurring across an exceptional range of depths as the descending slab continues bending into the mantle. Closer to the trench, powerful intraslab earthquakes have repeatedly demonstrated the system's strength. A magnitude 8.0 earthquake occurred during 2006, followed in 2009 by a magnitude 8.1 outer rise, normal fault earthquake generated seaward of the trench itself. Together, these events illustrated that large earthquakes arise not only along the plate boundary, but also within the deforming oceanic plate surrounding it. Across this single trench system, rapid convergence, immense depth, vigorous volcanism, and frequent seismic activity exist side by side. New Zealand, Fiji, Tonga, and Samoa all occupy a region shaped by these interacting processes where tsunamis, volcanic eruptions, and earthquakes originate from the same enduring tectonic framework. The landscape above the sea and the hidden terrain below remain linked through a boundary that continues carrying one plate beneath another with uncommon speed, sustaining one of the most geologically active environments on Earth's surface. For a brief interval during the early weeks of 2022, the boundary between ocean and sky seemed to disappear. Forces originating deep beneath the Pacific no longer confined themselves to the seafloor or the water above it. Instead, they expanded upward through the atmosphere, carrying the influence of the Tonga-Kermadec subduction system far beyond the horizon of any coastline. The event revealed that a trench capable of generating earthquakes and tsunamis could also disturb the air surrounding the entire planet. On January 15th, 2022, the submarine volcano Tonga Ha'apai produced the most powerful volcanic eruption directly observed during the satellite era. Rising from the volcanic arc created by subduction along the Tonga Trench, the eruption propelled an immense column of ash, water vapor, and volcanic gases approximately 57 miles into the mesosphere. Not since the eruption of Krakatoa during 1883 had Earth's atmosphere experienced an explosion of comparable scale, making the event an extraordinary moment for both volcanology and atmospheric science. The volcano itself possessed an unusually brief visible history. Although the volcanic system had existed beneath the sea for far longer, the island known as Tonga Ha'apai emerged above sea level only during eruptions in 2014. From a geological perspective, it represented a newly formed landscape assembled by the same subduction processes that had shaped the surrounding trench across millions of years. Within less than a decade, that young island became the setting for an eruption that fundamentally expanded scientific understanding of volcanic hazards. As magma rose rapidly through the submarine vent, it encountered enormous volumes of seawater. The interaction became intensely explosive because water transformed into steam almost instantaneously, expanding with tremendous force. This type of eruption, known as a phreatomagmatic explosion, fragmented magma into fine ash while releasing energy at an exceptional rate. The resulting blast generated not only powerful ocean waves, but also a pressure disturbance that surged outward through the atmosphere in every direction. Weather stations scattered across the globe soon began recording a remarkable signal. Sensitive barometers detected a rapid change in atmospheric pressure passing overhead, even at locations separated from Tonga by vast oceans and continents. The wave continued traveling around the planet, circling Earth 4 complete times before gradually fading into the background of normal atmospheric motion. Instruments within the United Kingdom recorded its arrival thousands of miles from the eruption. Scientists recognized the same rare phenomenon described after Krakatoa during 1883, yet no modern eruption had displayed it with such clarity through the worldwide network of contemporary observations. The ocean responded in ways that challenged established forecasting methods. Conventional tsunami models primarily estimate wave generation from sudden movement of the seafloor during earthquakes. Initial calculations based upon that framework suggested comparatively modest waves following the eruption. Actual observations revealed larger and faster arriving tsunamis because the traveling atmospheric pressure wave transferred additional energy into the ocean surface as it crossed entire basins. Rather than behaving solely as an earthquake-generated tsunami, the event became a coupled interaction between atmosphere and sea. In several locations, the waves reached coastlines before warning procedures designed around seismic information had fully interpreted the unusual sequence of events. The islands nearest the eruption experienced the greatest consequences. Across Tonga, communications were disrupted for days as ash-blanketed communities and underwater cables were damaged. Coastlines endured destructive waves arriving from an event whose behavior differed significantly from more familiar tectonic tsunamis. The young island of Hungaha'apai, built only a few years earlier through repeated volcanic eruptions, was itself largely destroyed during the explosion that carried its name across the scientific world. Long after the ash settled, the eruption continued influencing research into natural hazards. Scientists formally recognized the importance of volcanically generated atmospheric tsunamis as a distinct category, requiring dedicated study and improved forecasting methods. Existing warning systems had been developed chiefly around earthquakes and conventional seafloor displacement, not around pressure waves racing through the atmosphere before coupling with the ocean across immense distances. Within the Tonga-Kermadec system, one extraordinary eruption demonstrated that the pathways connecting Earth's interior, the sea, and the sky are more closely linked than previously understood, revealing another expression of the restless forces operating beneath the Pacific. Depth alone offers an incomplete way to understand the hidden architecture of Earth's trenches. When each of the great subduction systems is examined using the same geological standards, a different hierarchy gradually emerges. The decisive characteristics are not measured by the distance from sea level to the trench floor, but by the strength with which tectonic plates remain coupled, the nature of the sediments carried into the fault, the speed of plate convergence, the geometry that permits rupture to approach the seafloor, and the number of people living within reach of the resulting hazards. Together, these factors determine whether a trench remains largely a scientific curiosity or becomes a source of consequences extending far beyond its own coastline. Viewed through that framework, the Sunda Trench consistently occupies the highest level of concern. Its strongly coupled plate boundary stores enormous strain, while thick accumulations of sediment encourage rupture to propagate all the way to the ocean floor. That combination greatly enhances the generation of tsunamis. Surrounding the Indian Ocean are hundreds of millions of people connected by coastlines, vulnerable to waves crossing the basin. Across nearly every meaningful geological measure, the Sunda system possesses conditions favorable for producing some of Earth's largest natural disasters. The Japan Trench follows closely behind for different, though equally compelling, reasons. There, strong coupling combines with unusually thin layers of clay that reduce resistance near the shallow portion of the fault during major ruptures. That property allows sections of the megathrust to slip much closer to the trench itself, efficiently displacing seawater above. Japan's position along the western Pacific, together with the broader Pacific basin beyond, places extensive populations within the reach of tsunamis generated by this remarkably efficient tectonic system. The Aleutian Trench presents another expression of large-scale hazard. Extending across roughly 2,500 miles of convergent margin, it contains numerous rupture segments that have produced major earthquakes throughout both historical records and much older geological archives. Its orientation directs tsunami energy toward Hawaii and portions of the western coast of North America with unusual efficiency. Recent discoveries suggesting that a presently creeping section may also produce great earthquakes add another layer of complexity, demonstrating that assumptions based only upon modern measurements do not always capture the full behavior of a fault across centuries. The Puerto Rico Trench introduces additional hazards beyond conventional megathrust earthquakes. Oblique convergence creates an intricate mixture of fault types, while the strongest negative gravity anomaly on Earth reflects extraordinary processes unfolding beneath the Atlantic seafloor. Along its steep carbonate platform, enormous submarine landslides possess the capacity to generate tsunamis independent of major fault rupture. Approximately 4 million citizens of the United States live within the nearest zone influenced by this tectonic system, where several geological mechanisms may operate together rather than separately. Farther across the Pacific, the Tonga-Kermadec Trench combines the fastest plate convergence, presently measured, with the world's most active region of deep earthquakes and an extensive volcanic arc generated by continuing subduction. The eruption of Tonga Ha'apai demonstrated that hazards originating from this system may involve interactions between the ocean and the atmosphere, that conventional warning strategies were never designed to anticipate. Earthquakes, volcanism, atmospheric pressure, waves, and tsunamis all emerge from the same underlying tectonic engine. Placed beside these systems, the Mariana Trench presents a markedly different geological character. Although it remains the deepest known location in the ocean, its plate boundary is only weakly coupled. The descending plate follows a steep path that limits the area of frictional contact where large stresses typically accumulate. No documented historical megathrust tsunami has originated from the trench, and its location lies comparatively distant from the world's largest population centers. By every major hazard criterion considered throughout this journey, it ranks substantially lower than its dramatic depth might suggest. Broad comparisons of subduction zones reinforce this pattern. Global studies indicate that earthquakes measuring magnitude 7.5 and greater occur preferentially where the plate interface remains comparatively smooth, allowing extensive sections of the fault to lock together before rupturing. Rough subducting seafloor promotes weaker coupling and more gradual creep. The Izu-Bonin-Mariana system belongs overwhelmingly to this rough category, whereas the Japan-Kuril-Kamchatka margin is dominated by smoother interfaces capable of generating the greatest earthquakes. Judged by the processes that reshape coastlines within minutes, rather than by the depth of the ocean alone, the Mariana Trench no longer stands at the top of the list. Far from land, a tsunami gives almost no hint of the immense energy it carries. The ocean's surface remains remarkably ordinary, rising perhaps only 1 or 2 feet above its usual level before settling again with almost no dramatic appearance. Unlike the steep, breaking waves familiar along beaches, a tsunami is defined by extraordinary length rather than exceptional height. From one crest to the next, a single wave may extend across nearly 300 miles of open water, carrying its energy over distances so vast that the sea seems almost unchanged to anyone passing above it. A vessel crossing the deep ocean during the passage of such a wave might experience little more than a gentle lift and descent. The crew would likely continue their voyage without realizing that an immense pulse had moved beneath them. This surprising behavior reflects the unique physics of a tsunami. Ordinary wind-driven waves disturb only the upper portion of the ocean, with their influence fading rapidly below the surface. A tsunami behaves differently because the disturbance extends through the entire water column, from the surface all the way to the seafloor. Every layer of water participates in the motion together, allowing the wave to transport enormous amounts of energy across entire ocean basins with relatively little loss. The speed of that movement depends primarily upon water depth. Above the deepest portions of the ocean, especially where trenches descend into the Earth's crust, tsunami waves may travel close to 500 miles per hour, comparable to the cruising speed of a commercial passenger aircraft. Their progress is not driven by wind, but by gravity, acting upon an immense volume of displaced water. Once generated, The wave continues outward across the ocean until changing depth begins reshaping its character. As the tsunami approaches continental shelves and coastal waters, the transformation begins gradually. The decreasing depth slows the front of the wave because the seafloor increasingly influences its motion. Yet the tremendous energy contained within the moving water has nowhere to disappear. Instead, the wavelength shortens while the water rises higher. The broad, almost imperceptible pulse that crossed the open ocean begins compressing into a much steeper form. A wave standing only a foot or two above normal sea level offshore may eventually build into water levels reaching 30, 50, or even 100 feet along favorable coastlines, depending upon local geography and the amount of incoming energy. Sometimes the first visible sign does not resemble an advancing wave at all. If the trough reaches shore before the crest, the sea may withdraw rapidly from the coastline, exposing rocks, reefs, and stretches of seafloor rarely seen outside exceptionally low tides. Fish may remain stranded upon the exposed bottom, while boats settle awkwardly against harbor sediments. Throughout history, this unexpected retreat has drawn curious people toward the newly uncovered landscape. Repeated disasters have shown that such moments often precede the arrival of far more dangerous water, only minutes later, turning fascination into irreversible tragedy. Another widespread misunderstanding involves the number of waves. A tsunami almost never arrives as a single event. Instead, it commonly reaches shore as a sequence of surges separated by intervals ranging from roughly 10 to 40 minutes. The first arrival is not necessarily the largest. In many historical disasters, later waves have exceeded the initial surge in height and destructive force. People returning too soon after the first inundation have repeatedly encountered subsequent waves, still carrying tremendous energy across the coast. The shape of the receiving shoreline ultimately determines how that energy is distributed. Broad continental shelves can amplify rising water by forcing the incoming wave to compress across long distances. Narrow bays and harbor entrances may concentrate the flow into powerful surges that accelerate through confined channels. Along the deeply indented Sanriku coastline of Japan, generations have witnessed this natural funneling effect transform incoming tsunamis into devastating currents capable of reaching far inland. Across every ocean, touched by great subduction zones, the same physical principles remain unchanged. A tsunami is not defined by a towering wall of water racing across the deep sea, but by an almost invisible transfer of energy that reveals its full scale only when the ocean finally meets the land. Human history preserves only a small fraction of Earth's memory. Written chronicles fade with time, cities disappear, languages change, and entire civilizations pass beyond remembrance. Yet beneath coastal marshes, sheltered estuaries, tranquil lake bottoms, and the layered sediments of the seafloor, another archive continues accumulating without interruption. Each grain settles into place with remarkable patience, preserving evidence of events that unfolded long before any observer could have described them with ink or stone. When a great tsunami sweeps across the land, it carries far more than water. Sand from the shoreline, fragments of shells, pieces of coral, marine microorganisms, and salts from the sea are transported far beyond their ordinary limits before being left behind as the water retreats. Those deposits remain buried beneath younger sediments, forming thin but distinctive layers that differ clearly from the soils above and below them. In many locations, these marine signatures extend miles inland, reaching places where ordinary tides and storms could never carry them. Geologists searching through coastal landscapes have learned to read these layers, much like the pages of a carefully preserved manuscript. Along the shores bordering Sumatra, across the deeply indented Sanriku coastline of Japan, and throughout islands near the Aleutian Arc, excavations repeatedly uncover stacked sequences of tsunami deposits. Each layer represents another great inundation, separated from the next by decades or centuries of comparatively ordinary sediment accumulation. Differences in grain size, mineral composition, microscopic marine organisms, and chemical characteristics allow researchers to distinguish one ancient event from another, gradually assembling timelines extending across thousands of years. Far offshore, another archive develops within the depths themselves. Powerful earthquake shaking destabilizes sediments resting upon steep submarine slopes, sending dense underwater flows racing through submarine valleys before they finally settle into broad sheets known as turbidites. Each layer records a sudden episode of seafloor disturbance, rather than the slow settling that dominates most of the geological record. By extracting long sediment cores and counting these distinctive deposits, scientists have reconstructed histories of repeated great earthquakes reaching far beyond written documentation. Near the Japan Trench, these records include evidence of the Jogan earthquake during 869, whose tsunami spread across the coast in a pattern strikingly similar to the catastrophe experienced during 2011. Comparable discoveries have transformed understanding of the Aleutian Trench. Tsunami deposits preserved across the eastern Aleutian Islands and even within parts of Hawaii reveal a succession of prehistoric events during the 14th, 15th, and 18th centuries. When these deposits are combined with numerical modeling and geological mapping, they indicate megathrust ruptures involving approximately 72 to 105 feet of slip. Some of these prehistoric earthquakes exceeded anything preserved within modern historical observations, demonstrating that the instrumental record represents only a brief glimpse of the trench's much longer behavior. The Sunda Trench preserves an equally expansive memory. Researchers examining ancient coastal deposits have identified evidence of enormous tsunamis predating written history, including marine sand carried inland to elevations exceeding those reached during the disaster of 2004. These buried layers suggest that even one of the most devastating modern tsunamis may not represent the greatest event the Sunda system has produced. The geological archive continually widens the perspective offered by historical experience, revealing that exceptionally destructive earthquakes have returned repeatedly across immense spans of time. Taken together, these records reveal an important pattern. Great megathrust earthquakes along the world's most hazardous trenches generally recur over intervals measured in hundreds rather than thousands of years. A rupture during 2004 or 2011 does not conclude the geological story. Instead, it becomes another entry within a sequence that has unfolded repeatedly as tectonic plates continue their patient movement beneath the oceans. Unlike human memory, the ocean floor does not forget. Every major rupture, every submarine landslide, every surge that carried the sea beyond its ordinary boundary leaves another carefully preserved signature beneath later sediments. While libraries may burn and monuments may erode, these natural archives continue accumulating beneath water and along the coast, maintaining an uninterrupted record written not in words, but in layers of earth patiently arranged across millions of years. Every major advance in tsunami warning has followed a tragedy rather than preceded it. Instruments improved because coastlines had already been flooded, records expanded because lives had already been lost, and each generation inherited a monitoring system shaped by lessons written in seawater. The network surrounding today's oceans represents an extraordinary achievement of science and international cooperation, yet it remains constrained by the same physical laws governing the trenches themselves. The foundation of the modern Pacific Tsunami Warning Network can be traced to the Aleutian earthquake during 1946. Seismographs recorded the earthquake long before destructive waves crossed the Pacific and struck Hawaii. Researchers later recognized that the earthquake had been detected with sufficient time for warnings to have been issued if communication systems and organized response procedures had existed. From that realization grew a coordinated effort to transform distant seismic observations into practical warnings capable of protecting communities separated from an earthquake by thousands of miles. That effort gradually expanded into a global observing system, extending across many of Earth's oceans. Seismograph networks continuously measure ground motion, allowing scientists to determine the location, depth, and approximate size of earthquakes within minutes. Deep ocean pressure sensors, known as deep ocean assessment and reporting of tsunamis, stations monitor subtle changes occurring far below the sea surface. Global Positioning System-based deformation measurements track slow movement of Earth's crust, while coastal tide gauges verify changing sea levels as tsunami waves approach populated shorelines. Together, these independent observations provide multiple streams of information describing the earliest stages of a developing hazard. Among these instruments, the deep ocean pressure stations perform one of the most remarkable tasks. Resting upon the seafloor beneath thousands of feet of water, they detect minute changes in pressure caused by the passage of a tsunami overhead. Although the wave may remain almost imperceptible at the surface, the immense column of water above the sensor becomes slightly heavier and then lighter as the long pulse moves across the ocean. Once the measurements confirm a consistent signal, information is transmitted through surface buoys and satellites to warning centers in Hawaii and Alaska, where computer models estimate arrival times and expected wave heights across distant coastlines. For tsunamis crossing broad ocean basins, this system performs remarkably well. When waves require many hours to travel from their source to vulnerable communities, scientists have valuable time to analyze incoming observations, compare multiple forecast models, and distribute warnings through national emergency agencies. Entire coastlines may receive notice well before the first surge reaches land, allowing evacuations that have repeatedly prevented far greater losses of life. The greatest challenge appears when the earthquake occurs immediately offshore. In these near-field events, the interval between rupture and coastal impact may be less than 15 minutes. No monitoring technology can overcome the simple reality that the wave has very little distance to travel. During the catastrophe affecting Aceh province in 2004 and again along the Sanriku coast during 2011, some communities received little or no meaningful warning before the sea arrived. Instruments detected the events, yet the available time remained shorter than the time required to communicate, interpret, and respond. The eruption of Hunga Tonga Hunga Ha'apai during 2022 revealed a different limitation altogether. Existing warning algorithms had been designed primarily around earthquakes and conventional seafloor displacement. Instead, the eruption generated a rapidly moving atmospheric pressure wave that coupled with the ocean and altered tsunami behavior in ways not fully represented within standard forecasting models. Some coastlines experienced wave arrivals earlier than anticipated because the atmosphere itself became part of the hazard. Even the most advanced systems cannot perfectly anticipate every possibility. Japan maintains one of the world's most sophisticated tsunami warning infrastructures, yet the waves during 2011 exceeded official expectations in several locations despite rapid warnings. Another uncertainty remains within seismic gaps, fault segments that appear locked and continue accumulating strain without having ruptured during the historical record. Scientists can identify these regions, estimate their potential, and monitor their gradual deformation, but no observation can reveal the exact moment a fault will fail, how much of it will rupture together, or whether the break will extend toward the shallow portion capable of producing the largest tsunamis. Warning systems have transformed humanity's ability to respond, but the trenches continue operating according to geological time, while every alert must still unfold within the much shorter rhythm of human decision. Across the margins of the world's great trenches, survival has never depended upon instruments alone. Long before satellites orbited overhead or computers modeled distant earthquakes, families observed the rhythms of the land, remembered unusual floods, and passed those memories across generations. Their knowledge did not emerge from abstract study. It developed through repeated encounters with landscapes where the boundary between ordinary days and extraordinary events could change within moments, leaving experience itself to become part of the inheritance of a community. Along Japan's Sanriku coast, that inheritance can still be found carved into stone, scattered across hillsides overlooking the sea stand, weathered markers placed centuries ago by people who witnessed devastating tsunamis and wished to speak to descendants they would never meet. Some carry direct instructions advising future generations not to build homes below the stones. The messages are remarkably simple, yet they preserve the accumulated experience of repeated disasters more effectively than many written chronicles. Over time, different communities responded in different ways. Some villages continued rebuilding on higher ground, allowing the ancient warnings to remain practical guides rather than historical monuments. Others gradually expanded toward lower elevations, as memories faded and confidence grew that the sea would remain within familiar limits. Following the tsunami during 2011, researchers observed that several settlements, which had continued respecting those traditional boundaries, suffered far fewer losses than neighboring communities constructed below the old markers. The stones had not predicted the date of the disaster. Instead, they had preserved an understanding of where the water had reached before and where it could reach again. Modern Japan has increasingly woven this traditional knowledge into contemporary planning. Areas recognized as low ground have become central to official evacuation mapping, and lessons once transmitted primarily through local memory now influence engineering decisions, hazard education, and community preparedness. Rather than replacing inherited wisdom, scientific analysis has often confirmed the remarkable accuracy of observations preserved across centuries. Far across the Indian Ocean, different traditions carried similar meanings. In parts of Sumatra and neighboring coastlines, oral histories described occasions when the sea retreated with unusual speed before returning across the land with overwhelming force. These accounts were passed from elders to younger generations through stories, ceremonies, and daily conversation rather than permanent inscriptions. During the catastrophe of 2004, some communities recognized the rapidly receding shoreline as an unmistakable warning rather than an invitation to explore the newly exposed seafloor. Places where that knowledge remained active experienced higher rates of survival because people moved inland without waiting for official instructions. The Aleutian Islands preserve another long relationship between people and tectonic landscapes. For thousands of years, the Unangan people established settlements beside one of Earth's most productive tsunami, generating margins while carefully selecting elevated locations that reduced exposure to coastal flooding. Their oral traditions describe powerful waves and changing shorelines in ways that correspond closely with geological evidence recovered from coastal sediments. Archaeological discoveries indicate that several Aleutian communities have remained continuously inhabited for more than 9,000 years, demonstrating an enduring partnership between cultural memory and environmental observation beside an exceptionally active plate boundary. The Caribbean presents a different picture. North of densely populated islands, the Puerto Rico Trench extends beneath the Atlantic, while earthquakes remain familiar elements of regional history. Yet, public awareness of tsunami hazards has often received less attention than the broader seismic risk itself. This uneven balance between geological reality and collective memory creates its own vulnerability, because communities cannot respond effectively to dangers that occupy only a small place within everyday understanding. Across these distant coastlines, languages, beliefs, and traditions differ greatly, yet a common pattern appears. Scientific investigations recover ancient evidence from sediments, coral deposits, and fault structures, while communities preserve many of the same lessons through stories, settlement choices, landmarks, and shared experience. Each approach records a different part of the same history. Together, they reveal that adaptation is not achieved through technology alone, but through memory carried forward across generations. The trenches continue their patient movement beneath the oceans, and the people who have lived beside them the longest have often learned that remembering the past is itself one of the most enduring forms of preparation. Not every portion of a great fault moves at the same moment. Along the immense boundaries where one tectonic plate descends beneath another, earthquakes often rupture only part of the interface, leaving neighboring sections unchanged. Those untouched stretches continue gripping the opposing plate, storing strain while adjacent segments have already released theirs. Geologists refer to these lingering sections as seismic gaps, not because they are empty, but because their recent history remains incomplete. They represent places where Earth's long conversation with itself has paused rather than ended. A seismic gap does not announce that an earthquake will occur tomorrow or even within a human lifetime. The concept carries no calendar and offers no precise prediction. Instead, it identifies regions where measurements indicate that motion between tectonic plates continues while the fault itself remains locked. As years become decades and decades become centuries, the imbalance grows more significant. Each passing interval without a major rupture encourages scientists to examine the segment more carefully, because accumulated strain has not yet found a path toward release. South of the enormous rupture that transformed the Indian Ocean during 2004 lies one of the most closely watched examples, the Mentawai segment of the Sunda Trench. Geodetic measurements show that much of this boundary remains strongly locked despite the neighboring earthquake. Historical records indicate that the segment last experienced a major rupture during 1797, leaving centuries of continued plate motion to accumulate additional strain. Modern satellite observations reveal that the islands above the fault continue moving gradually as the underlying plates press against one another, providing direct evidence that deformation remains ongoing beneath the surface. The Aleutian Trench presents a more intricate pattern. Among the segments drawing particular attention are the Shumagan and Semiti regions, both of which have long occupied an important place within discussions of seismic hazard. During 2020, a magnitude 7.8 earthquake occurred within the Shumagan area, releasing part of the accumulated stress while leaving substantial portions of the surrounding fault still unbroken. Geological investigations extending beyond written history suggest that the eastern Aleutian margin possesses the capacity for much larger ruptures involving multiple connected segments. Such an event has not been documented during the relatively brief period of instrumental observation, yet coastal sediments and tsunami deposits indicate that the fault has behaved differently across longer spans of time. Along the Japan Trench, attention has gradually shifted toward areas immediately south of the rupture that occurred during 2011. Calculations of crustal deformation indicate that stress increased within neighboring sections after the Great Earthquake redistributed forces along the plate boundary. Although these changes do not guarantee another large event, they illustrate how one rupture can alter conditions far beyond the portion of the fault that actually slipped. Rather than ending the tectonic process, a major earthquake often rearranges the pattern of stress throughout the surrounding margin. North of the Caribbean islands, the Puerto Rico Trench remains among the least understood systems considered throughout this journey. Detailed monitoring networks are less extensive than those surrounding several Pacific subduction zones, while the historical record contains no well-documented modern megathrust earthquake comparable to those observed elsewhere. Even so, geological structure, geodetic measurements, and continuing plate motion together suggest that strain continues accumulating beneath the northern Caribbean. The absence of a recent catastrophe does not imply the absence of tectonic activity. In some respects, limited historical experience makes careful observation even more important. These examples reveal that seismic gaps are neither predictions nor mysteries awaiting dramatic revelation. They are measurable expressions of an unfinished geological process, identified through observations of fault behavior accumulated across generations of research. The ocean floor records where energy has already been released and where it continues gathering beneath immense pressure. Every trench carries portions that have recently shifted and others that remain firmly locked, preserving strain within the deep boundary between converging plates. Over geological time, those differences rarely remain permanent. The ledger of plate motion continues expanding with every passing year, and each locked segment becomes another reminder that Earth's most powerful processes unfold according to rhythms far older than human memory. Far below the reach of storms, and beyond the last traces of sunlight, another world unfolds beside the great trenches. Here, life does not measure time by changing seasons or daylight. Instead, it exists within landscapes, continually reshaped by the slow movement of tectonic plates, sudden earthquakes, and the gradual settling of sediments from oceans far above. The same geological forces capable of transforming distant coastlines also create conditions that sustain some of the most remarkable ecosystems ever discovered. The earthquake that struck the Japan Trench during 2011 altered far more than the coastline. At the bottom of the trench, the violent shaking destabilized immense quantities of fine-grained surface sediment that had accumulated over many years. Rich in freshly deposited organic material, this sediment cascaded into the Hadal depths, carrying more than 1 teragram of organic carbon into the deepest basin in a matter of minutes. What normally would have arrived gradually over long periods instead descended almost at once, fundamentally changing the chemistry of the trench floor. The biological community inhabiting those depths suddenly encountered an abundance of nutrients, unlike the steady background supply upon which it had previously depended. This relationship between earthquakes and biology extends throughout the Hadal Zone, the realm lying deeper than approximately 20,000 feet beneath the ocean's surface. Food is scarce at such depths because sunlight never penetrates far enough to support photosynthesis. Most nourishment arrives as tiny fragments of organic matter drifting downward from productive waters above. Along active subduction zones, however, powerful earthquakes periodically interrupt that slow descent. Tremors trigger underwater landslides, remobilize sediments, and deliver concentrated pulses of organic material into the deepest parts of the trenches. Geological activity, therefore, becomes an essential contributor to the deep ocean food supply, adding sudden episodes of abundance to an otherwise gradual cycle. Among the most successful inhabitants of these environments are amphipods, small crustaceans that flourish within the Tonga-Kermadec trenches. Their numbers can reach astonishing levels. Scientists deploying baited traps at depths exceeding 28,500 feet have recovered as many as 17,800 individuals within a single collection. Such extraordinary concentrations reflect more than simple adaptation to pressure. The abundance of these animals closely follows changes in sediment chemistry, demonstrating that the geological character of each trench directly influences the biological communities developing upon its floor. Along the Aleutian Trench, another connection between geology and life becomes apparent. Parallel to the subduction zone stretches a chain of volcanoes whose activity introduces heat and mineral-rich fluids into surrounding waters. These conditions support communities of chemosynthetic organisms that obtain energy not from sunlight, but from chemical reactions involving compounds released by Earth's interior. Instead of depending upon photosynthesis, they build entire ecosystems upon geological processes occurring beneath the seafloor. The same tectonic engine responsible for generating powerful earthquakes also supplies the chemical ingredients supporting these specialized forms of life. North of the Caribbean, investigations within the Puerto Rico Trench have revealed extensive microbial communities living among deep sediments under immense pressure. These microscopic organisms metabolize chemical compounds buried within the seabed, contributing to a global carbon cycle that researchers are only beginning to understand. Their activity appears closely linked to the tectonic environment that created the trench itself, where fault movement, sediment transport, and fluid circulation continually influence the chemical landscape surrounding them. Across all of these trenches, evolution has not unfolded apart from geological instability. Instead, living organisms have gradually adapted to recurring disturbance, incorporating the consequences of earthquakes, sediment flows, volcanic outgassing, and deep crustal chemistry into their own ecological relationships. Species prosper because the environment changes, not despite those changes. Nutrient pulses become opportunities, freshly deposited sediments become habitat, and chemical gradients produced by tectonic activity become sources of energy, sustaining entire food webs. Seen from the surface, these trenches often appear only as places of exceptional hazard, yet within their deepest reaches, they also nurture ecosystems found nowhere else on Earth. The immense forces stored beneath converging tectonic plates shape coastlines, redirect oceans, and occasionally transform human history. At the same time, those very forces sustain hidden biological worlds whose existence depends upon the restless geology unfolding beneath the sea, revealing that Earth's greatest engines of destruction are also remarkable engines of creation. Maps, measurements, and mathematical models have given humanity an extraordinary ability to observe the restless boundaries beneath the oceans, Satellites detect movements measured in fractions of an inch. Seismographs record vibrations traveling through the entire planet. Computers simulate countless rupture scenarios across faults extending for hundreds of miles. Even with these remarkable tools, one boundary remains beyond present understanding. Science can describe where strain is accumulating with increasing precision, yet it cannot determine the exact day or hour when that accumulated energy will finally be released. This distinction lies at the heart of modern seismology. Earthquake prediction, in its strict scientific meaning, requires identifying a specific location, a specific event, and a specific time before the rupture occurs. Decades of research have explored possible warning signs, including subtle ground deformation, changes in underground fluids, unusual seismic activity, and variations in electrical or magnetic properties. None has consistently provided the precision necessary to forecast individual earthquakes. The physical system governing fault rupture is extraordinarily complex, influenced by countless interacting conditions extending across enormous sections of Earth's crust. Minute differences within those conditions may influence how and when a fault ultimately fails, placing exact prediction beyond the reach of present knowledge. Instead, researchers rely upon probabilistic hazard assessment. Rather than asking precisely when an earthquake will occur, they evaluate how likely a fault is to produce a major rupture over periods measured in years or decades. Geological history, fault geometry, plate motion, locking behavior, accumulated strain, and records preserved within sediments all contribute to these assessments. The resulting probabilities guide building standards, emergency planning, infrastructure design, and long-term risk management. They do not function as forecasts announcing an approaching earthquake, but as carefully developed estimates describing the level of hazard a region faces over extended intervals. The earthquake along the Sunda Trench during 2004 illustrates this difference clearly. Geologists already understood that the fault possessed the capacity for an immense rupture. The possibility itself was never considered impossible or unexpected. What remained unknown was the precise moment when failure would begin, the extraordinary length of the rupture that ultimately unfolded, and the immense tsunami generated across the Indian Ocean. The event revealed that understanding geological capability is fundamentally different from anticipating the exact expression of that capability. A similar lesson emerged from the Japan Trench during 2011. Geological evidence had long demonstrated that the Sanriku coast had experienced devastating tsunamis throughout the centuries. The existence of future large earthquakes therefore surprised few researchers, yet several critical details lay outside prevailing expectations. Exceptionally large slip extended toward the trench axis. Tsunami heights surpassed many official maximum scenarios, and the resulting flooding produced consequences reaching beyond coastal communities into complex technological systems, including the nuclear emergency that followed. The earthquake expanded scientific understanding precisely because important aspects of its behavior differed from established models. Another continuing challenge involves tsunami earthquakes, unusual events in which tsunami size greatly exceeds expectations based upon earthquake magnitude alone. The Sanriku disaster during 1896 remains among the most striking examples. Although the earthquake itself measured approximately magnitude 7.2 and produced relatively modest ground shaking compared with many great earthquakes, the resulting tsunami exceeded 100 feet in some locations and claimed more than 22,000 lives. Such events demonstrate that earthquake magnitude alone cannot fully describe tsunami potential. encouraging continued research into the mechanics of shallow fault rupture and slow seismic release. The eruption of Tonga Ha'apai during 2022 introduced yet another unexpected chapter. Standard warning procedures had been developed primarily for earthquakes, generating conventional tsunamis through seafloor displacement. Instead, atmospheric pressure waves became an important part of the process, producing ocean responses that differed from established forecasting assumptions and reaching some coastlines sooner than anticipated. The event broadened scientific understanding by revealing a hazard that existing operational models had only partially represented. Each great earthquake, tsunami, or volcanic disturbance becomes both a natural disaster and a scientific experiment that cannot be repeated under controlled conditions. Every event strengthens understanding while exposing new uncertainties hidden within Earth's remarkably intricate systems. Modern science continues narrowing the distance between observation and understanding, yet the final step toward precise earthquake prediction remains elusive. For now, humanity can recognize where danger resides, estimate its long-term probability, and prepare with increasing wisdom while accepting that the exact moment when a great fault awakens still belongs to the deep and intricate workings of the planet itself. Viewed across a human lifetime, the Great Trenches seem like isolated places where extraordinary disasters occasionally unfold. Viewed across the lifetime of the planet, they become something very different. They are visible traces of an ancient engine that has been reshaping Earth's surface for billions of years, slowly rearranging continents, opening oceans, raising mountains, and carrying entire landscapes from creation to destruction and back again through an unending geological cycle. The motion begins far beneath the crust. Deep within the mantle, heat left from Earth's formation combines with the continuing decay of naturally occurring radioactive elements. That energy drives broad patterns of convection, causing hot material to rise while cooler material gradually sinks. Although these movements occur at speeds measured only in inches each year, they exert enough force to keep the tectonic plates in continual motion. Geological evidence indicates that this process has operated for at least 3 billion years, making plate tectonics one of the longest enduring systems shaping the surface of our world. Every continent bears the imprint of that persistent motion. Ancient fragments of crust drifted across earlier oceans before colliding and joining together to form larger land masses. Mountain ranges rose where plates converged, while older ranges gradually wore away beneath wind, rain, and ice. Elsewhere, the crust stretched apart, allowing molten rock to emerge along mid-ocean ridges and create entirely new seafloor. Far from those spreading centers, older oceanic crust eventually returned to the mantle through subduction, disappearing beneath another plate after journeys lasting hundreds of millions of years. Earth continually recycles its outer shell, replacing ancient seafloor with new crust, while preserving almost none of the earliest ocean basins that once existed. The relationship between mountains and trenches becomes especially clear when following the history of the Indian Plate. Long before the devastating earthquake along the Sunda Trench during 2004, that same tectonic plate had already transformed another part of the world. Around 50 million years ago, the Indian landmass collided with the Eurasian plate after traveling steadily northward across an ancient ocean. Unable to descend because both masses consisted largely of buoyant continental crust, the collision compressed and uplifted enormous volumes of rock, giving rise to the Himalayas. The towering peaks that now define the highest mountain range on Earth owe their existence to the same tectonic system that continues driving subduction farther to the southeast. Mountains and megathrust earthquakes emerge from different expressions of the same planetary process. Far across the Pacific, another chapter of that process continues beneath the Tonga-Kermadec trenches. Subduction has persisted there for approximately 45 million years, steadily carrying sections of the Pacific plate into the mantle. The plate itself, immense though it appears upon modern maps, is not permanent. As millions upon millions of years pass, more of its oceanic crust will descend beneath surrounding continents and island arcs. Given enough geological time, the Pacific plate in its present form will eventually disappear, consumed piece by piece through the same mechanism that has already erased countless earlier ocean basins. Within this immense perspective, earthquakes assume a different meaning. Each rupture represents neither an isolated accident nor an unexpected interruption of an otherwise stable planet. Instead, it is a brief release of energy within a tectonic engine that has operated continuously across spans of time almost impossible to imagine. The intervals separating individual earthquakes may seem long to human societies, yet they form only fleeting moments within a process that has never truly paused. The same understanding extends across every tsunami, every altered coastline, and every sudden change recorded within the sediments of the deep ocean. These events are not signs that Earth's geological machinery has failed. They demonstrate that the machinery continues functioning according to the physical principles governing a dynamic planet. The trenches explored throughout this journey are not exceptional departures from Earth's history. They are enduring expressions of the forces that assembled continents, sculpted mountain ranges, renewed the ocean floor, and continue guiding the restless evolution of the world beneath our feet. A single lifetime is long enough to witness remarkable change, yet astonishingly brief when compared with the rhythms that govern the great trenches. Memories passed from parents to children may span a century. Written history reaches back only a few thousand years in many regions. Beneath the oceans, however, the processes shaping continents measure time in intervals so vast that entire civilizations appear as fleeting moments. This difference in scale influences not only how Earth behaves, but also how people understand the limits of its power. The Indian Ocean tsunami during 2004 remains the deadliest natural disaster of the 21st century, claiming approximately 230,000 lives across many nations. Within human memory, it stands as an almost unimaginable benchmark, yet the geological record surrounding the Sunda Trench tells a more expansive story. Layers of sand, marine sediments, and displaced coastal deposits preserved far beyond the reach of written history indicate that even larger ruptures have occurred along the same plate boundary. Those earlier events survive only because the landscape itself retained evidence after every witness had disappeared. The Japan Trench offers a similar lesson. The earthquake during 2011 reached magnitude 9.0, placing it among the largest earthquakes ever measured with modern instruments. Even so, geological investigations indicate that the subduction system remains capable, over exceptionally long recurrence intervals, of earthquakes approaching magnitude 9.2 or perhaps greater. Perspective arrives from another coastline altogether. During 1960, the Chilean subduction zone produced the largest instrumentally recorded earthquake, reaching magnitude 9.5. Although separated by vast distances, the Chilean, Japanese, and Sunda systems all belong to the same family of subduction margins, demonstrating what this style of tectonic boundary can ultimately achieve under the right geological conditions. Evidence from the Aleutian Trench extends the timeline even further. Modern earthquake catalogs describe only a tiny fraction of its history, while prehistoric tsunami deposits preserved across distant Pacific shorelines reveal events exceeding anything documented during recent centuries. Sedimentary records from Hawaii point toward an immense tsunami during the 14th century, whose effects appear greater than any event contained within the roughly 500 years of written historical observation. The ocean remembered an earthquake that no surviving document recorded, preserving its passage through layers of sand rather than through words. Human civilization itself occupies only a narrow portion of this immense chronology. Organized societies with extensive written records extend back approximately 6,000 years, an impressive span when viewed through history, yet remarkably brief beside recurrence intervals measured in hundreds, thousands, or even more than 2,000 years. On some subduction margins, every chronicle ever written, every city ever built, and every generation that has shared recorded memory together encompass only a handful of complete cycles separating the very largest earthquakes. Entire chapters of planetary behavior therefore unfold beyond the boundaries of direct human experience. Geology continually broadens that perspective. Rock layers, offshore sediments, fossil shorelines, and displaced coastal landscapes preserve evidence extending millions of years into the past. Across these immense archives, a consistent pattern emerges. The earthquakes and tsunamis remembered today represent only samples drawn from a much broader range of possibilities. Some events exceeded anything experienced during recorded history, while others occurred so long ago that only the Earth itself retains their signatures. The absence of living memory does not diminish their reality. Perhaps this understanding explains the enduring wisdom carved into the stone markers overlooking the Sanriku coast. Those monuments made no attempt to predict future earthquakes or assign dates to the next great wave. Instead, they recorded where the last catastrophe had reached and entrusted that knowledge to people who had not yet been born. The message acknowledged a truth that modern geology now reinforces with remarkable precision. Human lives pass quickly, civilizations rise and change, and written history remains incomplete. The planet continues following timescales vastly older than memory itself, leaving each generation the responsibility of preserving what it has learned before that knowledge once again slips beyond the horizon of living experience. Among all the places explored throughout this journey, one name has remained woven through every comparison. The Mariana Trench has long occupied a special place in the human imagination, becoming a symbol of ultimate depth and the enduring mystery of the deep ocean. That reputation is well deserved. Yet, after tracing the behavior of Earth's most hazardous subduction systems, the Mariana can now be viewed with greater clarity, appreciated not only for the remarkable qualities it possesses, but also for the equally important qualities it does not. No other point within the world's oceans descends farther than Challenger Deep. Pressure there exceeds 15,000 pounds per square inch, enough to compress ordinary materials with astonishing force. Temperatures remain only a few degrees above freezing, sunlight never arrives, and every organism inhabiting those depths has evolved under conditions unlike those experienced anywhere else on the planet. When Jacques Piccard and Don Walsh reached the bottom aboard the bathyscaphe Trieste during 1960, they entered an environment no human would visit again for 52 years. Even today, each expedition expands knowledge of a realm that remains among Earth's least explored frontiers. Its extraordinary depth did not arise by chance. The Mariana Trench owes much of its remarkable profile to a combination of geological circumstances found together in very few places. Positioned far from large continental landmasses and major river systems, it receives relatively little sediment compared with trenches bordering extensive coastlines. Without thick blankets of accumulated deposits filling its lowest reaches, the trench preserves an exceptionally deep basin. At the same time, fractures within the descending Pacific plate divide part of the plate into a comparatively narrow section capable of bending more sharply as it sinks beneath the overriding plate. That steeper descent contributes directly to the exceptional depth for which the trench is renowned. Ironically, many of the same characteristics responsible for creating such remarkable depth also help explain why the Mariana behaves differently from the subduction zones examined earlier. The descending plate follows a comparatively steep path, while the contact between the plates appears only weakly coupled across much of the boundary. Geological roughness along the subducting plate further reduces the tendency for enormous areas of the fault to lock together over long periods. As a result, strain is less likely to accumulate across the vast continuous surfaces required for the largest megathrust earthquakes. Despite persistent plate convergence, the Mariana interface has generated remarkably few earthquakes, reaching magnitude 8.0 or greater, when compared with several shallower trenches elsewhere around the Pacific. Its geological signature, therefore, remains remarkably consistent. Researchers do not view the Mariana as a boundary concealing an overlooked rupture of extraordinary size or storing an undiscovered tsunami capable of rivaling the great disasters examined throughout this story. Observations gathered through seismology, marine geology, and plate motion all point toward a system governed by different mechanical behavior. Earthquakes certainly occur there. Volcanic processes remain active, and the subduction zone continues reshaping the ocean floor. Yet the style of tectonic release differs fundamentally from the tightly locked margins where the greatest tsunamis are born. None of this reduces the trench's scientific importance. Challenger Deep continues revealing organisms adapted to crushing pressure and perpetual darkness. Chemical reactions within the forearc, including extensive serpentinization, offer valuable insight into interactions between seawater and Earth's mantle. The volcanic arc rising above the descending plate supports hydrothermal systems whose chemistry helps illuminate the circulation of fluids through the crust. Across the trench floor and surrounding slopes, many deep-water animals remain undescribed, their evolutionary histories still awaiting careful study through future expeditions. The Mariana Trench, therefore, deserves every measure of respect it has earned. It represents the deepest expression of the ocean, an unparalleled natural laboratory where geology, chemistry, and biology meet under extraordinary conditions. Yet depth and danger are not interchangeable ideas. The trenches that threaten the greatest earthquakes and tsunamis are those where plate boundaries remain more strongly coupled, where immense strain accumulates across broader fault surfaces, and where millions of people inhabit nearby coastlines. The Mariana reveals the deepest face of the ocean. The Sunda, Japan, Aleutian, Tonga-Kermadec, and Puerto Rico systems reveal the immense power released when Earth's tectonic engine stores energy before finally letting it go. A traveler crossing the open ocean usually sees only changing light upon the water, shifting clouds above, and the distant curve of the horizon. The sea gives little indication of the immense structures concealed beneath it. Its surface often appears uniform across hundreds of miles. Masking landscapes deeper than mountain ranges are tall and fault systems capable of releasing more energy than entire nations consume across generations. Much of Earth's most influential geology unfolds beyond ordinary sight, carrying on beneath waters that reveal almost nothing of the world below. The Sunda Trench offers perhaps the clearest example of this contrast. Across the tropical Indian Ocean, ships routinely passed above the plate boundary for decades before the earthquake of December 26, 2004. Nothing visible distinguished that stretch of sea from countless others nearby. Waves rose and fell according to wind rather than tectonics. Beneath nearly 18 miles of rock, however, the fault remained locked as the descending plate continued pressing against the overriding crust. The accumulated strain increased gradually through the passing years until a few minutes transformed a century of stored motion into one of the defining geological events of modern history. Before that morning, the ocean's appearance gave no hint of the immense process unfolding far below. Along the eastern margin of Japan, fishing vessels cross waters above the Japan Trench almost every day. Commercial shipping, research expeditions, and coastal communities coexist with one of the most closely studied subduction zones on Earth. Yet the seafloor cliff created during the earthquake of 2011 rests approximately 24,600 feet beneath the surface, where perpetual darkness conceals every detail from ordinary view. Only specialized scientific expeditions descending with purpose have observed the transformed landscape directly. For everyone else, the remarkable change exists only through measurements, photographs gathered by remote instruments, and the careful interpretation of researchers who traveled into the depths. North of Puerto Rico, another hidden feature stretches beneath one of the Caribbean's busiest maritime corridors. Cruise ships, cargo vessels, and countless smaller craft traverse those waters every year, their passengers often unaware that one of Earth's most pronounced negative gravity anomalies lies directly below. The unusual gravitational signature reflects deep geological structure rather than anything visible upon the sea itself. Ocean currents continue flowing across the region. Sunlight reflects from familiar blue water, and ordinary navigation proceeds without revealing the extraordinary tectonic architecture hidden beneath the shipping lanes. Farther north, the Aleutian Trench borders an island chain where communities have long lived alongside recurring earthquakes. Residents know the movements of the ground through direct experience, recognizing tremors as part of life within an active tectonic landscape. Yet the trench itself remains concealed beneath some of the North Pacific's most turbulent waters. Its outline cannot be traced from the surface, nor can passing mariners observe the immense boundary descending into the earth below. The geological feature defining the region exists almost entirely beyond ordinary human perception, understood through mapping, seismology, and generations of scientific exploration rather than through direct observation. Across the southwestern Pacific, the Tonga-Kermadec system descends nearly 36,000 feet beneath open ocean. Seen from above during ordinary conditions, its waters appear little different from countless other expanses of sea. Then, during January of 2022, an immense volcanic eruption temporarily replaced that familiar scene with a towering column rising approximately 57 miles into the atmosphere. For a brief interval, one of the planet's deepest geological systems announced its presence in spectacular fashion before the surface gradually returned to familiar appearance, leaving the underlying tectonic boundary concealed once more. Together, these trenches have reshaped coastlines, redirected ecosystems, transported sediments across immense depths, and preserved their histories within geological archives extending millions of years into the past. Their influence reaches far beyond the places where the plates actually meet. Yet from the deck of a passing vessel or the window of an aircraft, they remain almost impossible to recognize. The ocean carries extraordinary concealment, covering some of Earth's greatest geological forces beneath an outward appearance of remarkable simplicity. Much of the planet's enduring work unfolds beyond the reach of ordinary sight, reminding us that the landscapes shaping our world are often those least visible to the human eye. Imagine the world not as a collection of separate oceans and continents, but as a single connected sphere wrapped in moving plates. From that perspective, the great trenches explored throughout this journey no longer appear as isolated features scattered across distant seas. They become parts of one continuous pattern, linked by the same planetary engine and tracing an immense arc around much of the inhabited world. Beginning along the eastern margin of the Indian Ocean, the Sunda Trench follows the boundary where the Indo-Australian Plate descends beneath Southeast Asia. Far to the northeast, the Japan Trench marks another meeting place between converging plates along the western Pacific. The chain then continues into the broad curve of the Aleutian Trench, stretching across the northern Pacific toward Alaska. On the opposite side of the globe, the Puerto Rico Trench borders the northern edge of the Caribbean, extending the pattern into the Atlantic Ocean. Southward once more, the Tonga-Kermadec system reaches through the southwestern Pacific, completing another great segment of Earth's restless perimeter. Together, these systems surround much of the Pacific basin while extending their influence into both the Indian and Atlantic Oceans. Their locations reveal something remarkable about human geography. Many of the world's largest coastal populations occupy shores shaped directly or indirectly by these tectonic boundaries. Japan stands immediately above an active subduction zone. Much of Southeast Asia rises beside the Sunda system. The Hawaiian Islands occupy a central position within the Pacific, where tsunami energy generated by several trench systems may eventually converge. Along the eastern United States, coastlines remain connected through the Atlantic to hazards originating near the Puerto Rico Trench, while the western United States faces long-established relationships with the Aleutian Arc and the neighboring Cascadia subduction zone. Across thousands of miles, communities separated by language, culture, and history nevertheless share the same underlying geological framework. This broader arrangement forms much of what is commonly called the Ring of Fire, the vast horseshoe of earthquakes and volcanoes encircling the Pacific Ocean. Rather than existing as unrelated features, volcanoes, island arcs, deep trenches, and powerful earthquakes arise together because they reflect different expressions of subduction operating simultaneously along adjoining plate boundaries. Each trench occupies its own place within this larger network, contributing to a planetary pattern extending far beyond any individual coastline. Even so, these systems do not function as though connected by a common schedule. Each trench evolves according to its own geological history, fault geometry, plate motion, and accumulated strain. Great earthquakes generally occur independently, rather than passing from one trench to another in sequence. The immense Sunda earthquake during 2004 redistributed stress across parts of the planet and produced measurable seismic responses at great distances. Yet such extraordinary events remain exceptions rather than evidence of coordinated global ruptures. Most of the time, every subduction system follows its own rhythm across intervals measured in centuries or longer. When viewed collectively, however, their combined influence encompasses an extraordinary portion of modern civilization. Ports, fisheries, shipping routes, coastal cities, and island communities all exist within landscapes shaped by these converging plates. Generations have built homes, cultures, and economies beside oceans whose coastlines owe their very existence to tectonic forces operating beneath distant waters. Daily life unfolds upon terrain created through processes that continue beneath the surface, whether noticed or not. Geological records hint that there have been periods when several major trench systems experienced heightened activity within comparatively similar spans of time. Deep marine sediments and coastal deposits preserve evidence suggesting multiple shorelines were reshaped during overlapping geological intervals. These episodes remind us that Earth's history is not evenly paced, but marked by chapters in which profound changes occurred across widely separated regions before long intervals of relative stability returned. Taken together, the 5 trenches reveal something larger than the history of individual earthquakes or tsunamis. They outline the living architecture of a planet continually reorganizing its surface through plate tectonics. Continents drift, ocean floors are renewed, coastlines evolve, and deep boundaries continue their patient work beneath the sea. The trenches are not unusual interruptions within an otherwise stable Earth. They are enduring expressions of the same planetary process that has shaped the world from its earliest history and continues, inch by inch, to shape the world that exists today. Long before anyone measured ocean depths, mapped tectonic plates, or understood the hidden architecture beneath the sea, people settled along coastlines because the ocean offered abundance. Fish gathered in coastal waters, rivers met sheltered bays, trade crossed open horizons, and generations learned to build their lives where land and sea touched. Beneath those familiar shores, the great trenches were already moving with patient persistence. Their influence reached human history long before humanity possessed words to describe the forces responsible. There is no intention within these immense geological systems. A fault, in geological language, describes a fracture where rock moves against rock. It does not imply failure in the ordinary human sense of the word. The descending plates continue their slow passage because gravity, heat, pressure, and the physical properties of Earth's interior require them to do so. The ocean does not distinguish between villages and cities, between ancient settlements and modern skylines. It follows the same physical laws that govern the planet long before people stood beside its shores. Recognizing this changes the way the coastline itself appears. Harbors, beaches, river mouths, cliffs, and broad coastal plains often seem permanent because they endure across many human generations. Yet, every shoreline represents only one chapter within a much longer geological story. Far beneath the waves, plates continue advancing by inches each year, gradually altering the shape of the crust, supporting everything above. The movement is almost imperceptible from one year to the next, but over centuries and millennia, it reshapes landscapes, redirects rivers, raises mountains, lowers basins, and occasionally releases immense stores of accumulated energy in a matter of minutes. This understanding does not diminish the value of living beside the sea. Quite the opposite, it helps explain why people have continually returned to these places despite the risks. Coastal waters provide food, moderate climates, and pathways connecting distant cultures across vast oceans. Great ports became centers of knowledge as well as commerce. Languages spread aboard ships. Scientific discoveries traveled from continent to continent. Families established communities overlooking bays where generations before them had launched boats into the same waters. The relationship between humanity and the sea has always been shaped by both opportunity and uncertainty, neither one canceling the other. Knowledge, therefore, becomes one of the few enduring advantages available to civilization. Humanity cannot halt plate tectonics, prevent subduction, or persuade a locked fault to release its strain more gently. Those processes belong to the planet itself. Yet careful observation, geological research, engineering, historical memory, and thoughtful planning allow societies to reduce vulnerability. Every improvement in hazard assessment, every carefully designed building, every warning system, and every preserved account of earlier disasters represents another step toward living more wisely within a dynamic world. Understanding does not eliminate danger, but it creates possibilities that ignorance never can. Perhaps no example expresses this more gracefully than the stone markers overlooking the Sanriku coastline. They neither attempted to command the sea nor promised protection against every future disaster. Instead, they recorded where earlier waves had reached and entrusted that knowledge to generations still unseen. Their purpose rested upon continuity rather than certainty, preserving experience across spans of time longer than any individual life. Modern geology now arrives at remarkably similar conclusions through entirely different methods, reading the landscape, sediments, and fault systems, while reaching toward the same enduring lesson carried forward by those carved stones. The deepest value of studying these trenches extends beyond scientific curiosity alone. It encourages a broader understanding of humanity's place upon an active planet whose history vastly exceeds our own. Coastlines remain among Earth's most beautiful and life-sustaining environments precisely because tectonic forces have shaped them across immense spans of time. Those same forces continue their work beneath the oceans without pause or awareness. To know they are there, to understand how they operate, and to preserve that understanding for those who come after us is not an act of fear. It is an expression of respect for the remarkable planet that has always carried us, and for the generations who will one day inherit the same shores beneath the same enduring sea. The oldest measure of time is not found in calendars or monuments, but in movement so gradual that no single generation can perceive it. Continents drift without haste. Ocean basins widen and contract across spans beyond imagination. Beneath the sea, tectonic plates continue journeys that began long before forests covered the land in their present form, carrying fragments of Earth's surface across distances measured not by miles alone, but by immense chapters of planetary history. The Pacific Plate has remained in motion for more than 100 million years, traveling steadily as part of the planet's enduring cycle of creation and renewal. Along the Sunda margin, the Indian Plate has descended beneath Southeast Asia for tens of millions of years, gradually consuming ancient oceanic crust while building mountain ranges, volcanic arcs, and deep marine basins. Far across the southwestern Pacific, the Tonga-Kermadec system has remained active for roughly 45 million years, preserving one of Earth's longest-lasting expressions of subduction. Compared with these immense intervals, the approximately 6,000 years of human civilization occupy only the smallest fraction of an already unfinished geological sentence. Even the earthquake cycles that seem unimaginably long within human history appear remarkably brief beside the lifespan of the trenches themselves. Along several of the world's great subduction zones, the average interval separating the largest ruptures ranges from approximately 200 to 500 years, though every fault follows its own history, rather than an exact schedule. The rise of the industrial age, the development of electricity, aviation, global communication, and modern scientific observation together fit comfortably within a single recurrence interval on some of these boundaries. Much of recorded modern history occupies no more than 2 or 3 complete cycles of the largest earthquakes certain trenches have produced repeatedly across thousands of years. The ground preserves those repetitions with remarkable fidelity. Sediment layers deposited after the Indian Ocean tsunami during 2004 resemble much older deposits left behind by earlier waves crossing the same coastlines centuries before. Along northeastern Japan, evidence surrounding the earthquake during 2011 likewise joins older geological records indicating that comparable events visited the same shores long before written observation became possible. Successive layers accumulate one above another, each preserving another chapter within a narrative extending far beyond memory. The coastlines encountered by modern tsunamis were themselves shaped by countless predecessors whose names were never spoken because no surviving witness remained to describe them. This persistence reveals something fundamental about the planet. Geological systems possess no awareness of civilizations, governments, technologies, or generations. A subduction boundary does not accelerate because a coastline has become densely populated, nor does it postpone the gradual accumulation of strain until a more convenient century arrives. Rock continues responding to pressure according to physical law alone. The tempo belongs entirely to Earth, unfolding across intervals that bear little resemblance to the rhythms guiding politics, economics, or individual lives. Perhaps this difference explains why meaningful understanding requires unusual patience from those who study these places. Scientific knowledge grows through observations gathered across decades, historical records assembled across centuries, and geological evidence extending through millennia. No single lifetime can observe an entire earthquake cycle at every trench. Yet each generation contributes another carefully measured piece to a much larger record. The work resembles a relay extending across time, with each observer preserving information for successors who will continue the task after them. The stone markers overlooking the Sanriku coastline express this principle with remarkable simplicity. Their builders understood that the people reading the inscriptions centuries later would never know those who carved them. The message was intended to survive relationships, families, languages, and even governments, carrying practical memory farther than any living storyteller could. Modern geology follows the same aspiration through different tools, extending observation beyond individual experience and allowing evidence to speak across centuries. In the end, the enduring lesson offered by the Great Trenches is not merely that Earth changes, but that it changes according to timescales vastly exceeding our own. Human history unfolds within those longer rhythms rather than apart from them. The planet continues its patient work beneath the oceans, while each generation inherits the opportunity to observe carefully, remember faithfully, and pass forward what it has learned before another chapter of that immense story quietly becomes part of the past. A single measurement often becomes the identity of a place. One mountain is remembered because it is the tallest, one river because it is the longest, one trench because it reaches the greatest depth. Numbers offer satisfying order, arranging the natural world into lists that seem easy to understand. Yet the Earth rarely follows the categories people create for it. Beneath the surface, the qualities that matter most often remain hidden behind relationships, histories, and processes that no single figure can fully express. The Mariana Trench descends to approximately 36,000 feet, making it the deepest known point in the global ocean. The Sunda Trench reaches roughly 24,000 feet at its deepest locations, leaving a difference of about 12,000 feet between them. Judged only by depth, the Mariana appears unquestionably more extreme. That comparison is factually correct, yet it says remarkably little about how each trench influences the world above. Measured through consequences for coastlines, ecosystems, and human societies, the Sunda system occupies an entirely different place within Earth's geological story. Depth is appealing because it can be communicated with remarkable simplicity. A larger number naturally appears more impressive than a smaller one. From that comparison emerges an intuitive sequence in which deepest seems equivalent to greatest, greatest seems equivalent to most powerful, and most powerful appears equivalent to most dangerous. Nature, however, does not consistently reward that logic. The mechanics governing earthquakes, tsunamis, volcanism, and plate motion depend upon interactions that cannot be summarized by the depth of an ocean basin alone. The earthquake beneath the Japan Trench during 2011 illustrates this distinction with unusual clarity. During only a few minutes, portions of the seafloor shifted by approximately 164 feet, releasing enormous stored strain accumulated over centuries. That sudden movement displaced vast volumes of seawater and determined how rapidly tsunami waves formed and propagated toward the coast. The scale of that displacement cannot be inferred by examining the trench's depth. Instead, it emerged from the geometry of the fault, the physical properties of sediments near the plate boundary, and the long accumulation of tectonic stress preceding the rupture. Those invisible conditions shaped the outcome far more profoundly than the distance between the sea surface and the trench floor. North of Puerto Rico, another reminder lies concealed beneath familiar waters. The trench there contains the strongest known negative gravity anomaly on Earth, revealing that the distribution of mass beneath the crust differs substantially from surrounding regions. The resulting gravitational variation slightly alters the shape of the ocean surface across many miles, producing measurable effects that sophisticated navigation instruments must account for during careful surveys. Researchers continue investigating the precise combination of deep geological structures responsible for this remarkable anomaly. None of these characteristics become apparent by knowing the trench's maximum depth alone. Far across the southwestern Pacific, the Tonga-Kermadec system demonstrated another dimension of geological complexity during 2022. The extraordinary atmospheric eruption associated with Tonga Hapai generated pressure waves that traveled around the world several times, while ocean waves reached distant coastlines whose hazard models had not anticipated such behavior. The event reflected interactions between the descending plate, rising magma, seawater, and volcanic structure, rather than any simple ranking based upon how deep the neighboring trench extended beneath the sea. These examples point toward a broader truth. Oceans do not arrange themselves according to the categories people find most convenient. Geological systems evolve through physics, chemistry, material properties, pressure, temperature, and histories unfolding across millions of years. Human classifications remain valuable because they simplify communication and encourage discovery. Yet every classification leaves something important outside its boundaries. The Earth continues operating according to relationships more intricate than any list can fully capture. In the end, the number marking the deepest point within the Mariana Trench remains an extraordinary scientific fact. It tells us where the ocean reaches its greatest measured depth. It does not reveal which coastlines face the greatest geological hazards, which plate boundaries store the most strain, which volcanic systems possess the greatest capacity for global influence, or which histories remain written beneath layers of ancient sediment. Depth marks where the ocean ends. Understanding begins only after looking beyond that single number. Far beneath the familiar ocean traced by ships, tides, and weather, another ocean exists, one not made of water but of movement. It flows through rock instead of waves, advancing at a pace too gradual for ordinary perception, yet powerful enough to reshape continents across immense spans of time. Every shoreline, every island arc, every coastal plain discussed throughout this journey ultimately owes its existence to that hidden world beneath the seafloor, where Earth's deepest machinery continues its work without interruption. Beneath the eastern Indian Ocean, the Sunda megathrust has not reached an ending. Since the earthquake of December 26, 2004, the converging plates have continued advancing toward one another. Every passing year adds another small increment of motion. Most of that movement occurs without immediate release, becoming part of the gradual accumulation of strain characteristic of a subduction boundary. The earthquake entered history as a completed event, yet the geological process responsible for it never concluded. It simply continued beyond the horizon of human attention, following the same physical laws that governed it before any written account existed. Across the Pacific, the Japan Trench follows its own enduring rhythm. The remarkably thin, clay-rich layer near portions of the plate boundary, recognized as an important contributor to the extraordinary shallow slip during the earthquake of 2011, remains embedded within the fault zone today. It has not disappeared because its role in one earthquake has already been fulfilled. Instead, it continues existing as part of the geological structure itself, preserving the physical conditions that scientists now understand with far greater clarity than before. The plates above and below it continue their gradual convergence, each fraction of motion becoming another sentence within an immensely long geological narrative. Farther north, the Aleutian Arc extends approximately 2,500 miles across one of the most isolated, inhabited regions on Earth. Small earthquakes occur there almost every day, reflecting the continual adjustment of an active plate boundary. Most pass unnoticed beyond nearby communities and scientific monitoring networks. Yet the same subduction system possesses the ability to influence coastlines thousands of miles away through the movement of the surrounding ocean. The distant beaches reached by future waves need never glimpse the source beneath the North Pacific for that connection to remain entirely real. North of Puerto Rico, another remarkable landscape continues resting beneath Atlantic waters. The trench preserves its unusual gravitational character, towering submerged limestone escarpments, and the complex tectonic interactions that have made it among the least comprehensively surveyed of the world's major subduction systems. Millions of people live throughout the surrounding Caribbean while carrying on ordinary lives above a geological boundary many have never heard named. Beneath commercial shipping routes and familiar sea lanes, the fault continues evolving according to its own history rather than the awareness of those traveling overhead. Across the southwestern Pacific, the Tonga-Kermadec system remains one of Earth's most prolific producers of deep earthquakes. Every year, seismic activity ripples through descending slabs, reaching extraordinary depths within the mantle, providing scientists with invaluable observations about conditions impossible to examine directly. Above that descending plate, the volcanic arc continues drawing energy from processes unfolding far below the surface. During January of 2022, those interactions produced an eruption whose atmospheric effects exceeded anything instrumentally observed since systematic global monitoring began during the late 19th century, carrying volcanic material toward the edge of space while revealing capabilities few had fully anticipated. None of these systems waits in anticipation of some appointed future moment. They are already active. Their movements continue, whether measured or ignored, whether coastlines prosper or change, whether civilizations flourish or fade. Tens of millions of years shaped the boundaries explored throughout this story, and tens of millions more will almost certainly follow. Humanity lives not above a separate world, but upon the uppermost surface of this continuing geological engine. The familiar ocean reflects sunlight, carries ships, and sustains life, while beneath it another, deeper realm steadily guides the architecture of continents, the evolution of coastlines, and the forces that have accompanied every chapter of human history. At the end of this journey, one distinction remains more important than any measurement, map, or ranking. The Mariana Trench is the deepest place on Earth. It is not the most dangerous. Those two ideas are not interchangeable, and recognizing the difference changes the way the ocean itself is understood. Depth describes one remarkable characteristic. Geological influence arises from an entirely different set of processes, unfolding far beyond what a sounding line or depth chart can reveal. Across the hidden boundaries beneath the sea, the ocean floor preserves a continuous record of Earth's activity. Every descending plate, every layer of sediment, every uplifted ridge, and every buried fault reflects events stretching back through ages that preceded forests, mammals, and humanity itself. While civilizations appeared, flourished, and disappeared along changing coastlines, the deeper architecture of the planet continued evolving beneath them. Long before the first people stood beside the sea and looked toward the horizon, the foundations of those same shores were already being shaped by forces operating far below the waves. That story has never reached its final chapter. Plates continue their gradual movement. New sediments settle upon older ones, preserving another season, another century, another millennium within the growing archive beneath the ocean. Future geologists, whether human or otherwise, would find the traces of today's coastlines resting above older layers that recorded coastlines even more ancient. Each deposit becomes another page within a narrative extending across millions of years, written without language, yet preserving extraordinary precision for those able to interpret it. Nothing within these great trench systems exists as a warning deliberately directed toward humanity. They possess no intention, no preference, and no awareness of the countless lives unfolding overhead. They remain ancient geological boundaries, carrying out the same physical processes that have governed Earth's surface throughout immense spans of time. Humanity simply happens to build homes, cities, ports, and cultures upon a planet whose crust remains active beneath the oceans. The relationship exists because people inhabit the surface, shaped by those processes, not because the processes themselves acknowledge those living above. Among the most enduring expressions of that understanding stands a line of carved stone overlooking the Sanriku coast. The inscription does not attempt to explain plate tectonics, oceanography, or the mechanics of tsunami generation. It offers no reassurance and no elaborate philosophy. Instead, it marks a boundary established through lived experience, preserving a memory capable of outlasting those who first placed it there. Its message survives because it does not depend upon the identity of the reader. Every generation encounters the same stone beneath the same sky, inheriting knowledge carried forward across centuries with remarkable simplicity. Modern science extends that conversation using different tools while pursuing the same enduring purpose. Research vessels map the seafloor in extraordinary detail. Ocean bottom instruments record motions too small for ordinary perception. Satellites measure subtle changes in Earth's shape. Sediment cores recover histories, extending far beyond written records. Together, they reveal that the familiar ocean surface reflects only the upper expression of a much larger system whose deepest workings remain concealed beneath layers of water and rock. The more completely those hidden processes are understood, the more clearly the surface world itself begins to make sense. Throughout this exploration, the trenches have appeared as places of remarkable depth, extraordinary biology, immense geological power, and astonishing scientific discovery. Yet perhaps their greatest lesson lies not within any individual earthquake, eruption, or measurement, but within the continuity connecting them all. They remind us that Earth's history is ongoing rather than complete, unfolding beneath every coastline, whether noticed or ignored, measured or unmapped. The ocean has never been motionless. Beneath its changing surface, the planet continues shaping continents, coastlines, and the landscapes where human history unfolds. The deepest boundaries remain unseen by almost everyone who crosses above them, yet their influence reaches far beyond the darkness where they lie. What happens below the surface does not remain below the surface. In time, it rises,